qué manera de ver las cosas en el lado negativo.
Ahora te puedes resistir. ¿Por qué le vas a presentar?
Porque sintió feo. Y yo pensé que era muy buen chiste. ¿Sabes qué? ¿En dónde? Sí. Ah, bueno, con tu hijo.
No, Hernán y Elfego hablan solo en inglés, entre ellos.
Elfego también está con...
Sí, sí.
Entre ellos cuando tú no estás.
¿Sí?
¿A qué? Pero tú lo impones.
No.
Él lo impone, ¿ves lo que dice? No, y no hablan español. Bueno. ¿Yo? ¿Otra vez? Ya se me acabó la garganta. Bueno, entonces, no, ahorita lo voy a presentar como uno de mis más brillantes ex estudiantes para que no se quede. ¿Dónde está el micrófono? Y aquí lo apagamos, ¿no? Pero todavía no son las 3, falta un minuto. Ya está la transmisión. Bueno, déjame agarrar el cronómetro. ¿Cuánto tiempo antes quieres que te avise?
5 minutos.
5 minutos. Bueno, a los 20. Ok.
There is an announcement that in the program we have 3 hours of talks without break. So there has been a mutiny. I was asked by the committee of fighting committee that we should have a break after 3 talks. Do you agree?
Yes.
Very good. 5 minutes. No. Probably half an hour, right?
Well, or 15 minutes, Rafael. 15. By general consensus, 15 minutes. So it's my pleasure to introduce Rodrigo Ledesma, who is a former student on Facultad de Química, UNAM. So he did his undergraduate with me. And since he was very smart, I sent him to do his PhD with Aurora. And, well, as you will see, with the amount of natures that he has a very successful career. But, yeah, he was it. But we have not given the CV of all the speakers, so he came into, okay, he went to, you didn't send him to Oxford. He went to Julia Yeomans because actually he wanted to go where Rosana Collepardo had been. You know, I know better the story. So I will not give the CV of Rodrigo because it's not his symposium. But thank you very much.
Right, so thank you very much for that very kind introduction, and I feel I should reciprocate. I'd like to thank Eugenia and Rafael for this kind invitation. And I must say that I'm very proud and very happy to be here talking to you today. As Eugenia mentioned, I am a graduate from the Faculty of Chemistry, where I did my thesis with Eugenia, actually. And then I moved to Spain to work with Aurora, where I spent my years as a PhD student working on many aspects of wetting, doing numerical modeling. And one of the things that towards the end of my thesis we started to work on was to try to figure out how to produce droplets in new ways that could be useful for microfluidic applications. And so we ended up sort of developing what I think is perhaps the first smart surface that I studied in my career, which had to do with just using wetting properties and forcing in order to create droplets in a controlled manner. And that was a very nice study that we ended up publishing. But I think that one of the things that Felix mentioned earlier today is that Aurora was very clear about the promise that should we ever publish a big paper in a Nature journal, we would deserve a dinner in perhaps one of the Michelin star restaurants that you can find in Barcelona, and therefore I'm looking forward to dinner. So I'm really looking forward to that. But nevertheless,
Dinner to you, okay?
yeah. Well, she never paid. So I guess that the point that I want to make is that these ideas that appeal to me and that have later on formed one of the research lines that I'm working on today were originated as a PhD student when I was back in Barcelona, where I have many fond memories as a PhD student. So today I will talk about some of the stuff that I'm doing right now, and I have moved on to study a system which is inspired in a smart biological surface, which has to do with the surface of a plant which is called the pitcher plant. And many of you have probably seen this before. So the pitcher plant is actually a carnivorous plant that grows in the tropics, and it has this pitcher-like structure. And if you visit the plant on a dry day, what you'll see is that there are many ants and other bugs which are roaming about, and nothing interesting happens. But if you go back on a wet day, then what you see is the following: little ant goes in, goes in, goes in, and they meet a very grim end because, of course, inside that pitcher structure, what you find is a bunch of digestive juices. So sadly, that's the end of the ant, but that's the beginning of the bio-inspiration to develop a smart surface. So this has been around for some time, and the idea is the following: can we borrow inspiration from this biological system in order to create a surface which now has the ability to create a very slippery surface so that water droplets are able to sort of move about very easily. And therefore you reduce friction in the system, but you also create loads of applications that have to do, for example, with water repellency and self-cleaning, right? And there are many ways in which you can use this, in which you can create these surfaces, but they're all based in the same physical principle, which is you need some kind of porous material that you render hydrophobic by treating it with either chemically or with some nanostructure. And what you do next is that you infuse that material with a lubricant which is immiscible with the liquid that you want to repel. So if you want to repel water, then what you do is that you infuse that with an oil, for example, and we use silicone oil in the laboratory. And then what you see there, we actually used a student to model their hands there because mine are not as nice. But then you see a water droplet moving about very nicely on top of that surface. Right, so today I'm going to talk about 3 applications that we have been studying on this. And I think that the main philosophy that I want to sort of come back over and over is the idea that these systems, in a way, are rather simple, because as you know, when you talk about wetting interactions, one of the things that you really want to understand has to do with the idea of static friction, right? And static friction can be exemplified very clearly if you take a droplet on top of an ordinary surface and you begin to tilt the surface so that gravity starts to pull on the droplet, trying to make it roll. And what you see is that you will need to tilt your surface at a certain angle so that there is a certain deformation of the droplet, at which point the droplet will start to move. And that deformation defines these 2 angles that you can relate to the static friction that you need to overcome to create motion, and that has to do with the concept of contact angle hysteresis. So on ordinary surface, what you see is that the lower the surface tension of the liquid, the more you have to tilt your surface. And that is because the more affine the liquid will be towards that surface, so you have more static friction. But the amazing thing about these slippery surfaces is that what you see is that the contact angle hysteresis drops dramatically. And moreover, what you see is that it becomes independent of the surface tension of the liquid, which implies that there is some kind of decoupling of the liquid that you want to repel with the surface. So that idea is rather interesting because it means that you have some kind of wettability on the surface that doesn't quite depend on the surface tension of the liquid, which is trying to wet that surface. And there is definite proof that if you choose your liquid and solid, your liquid pairs and your solids carefully, then you can actually create a thin film that separates the droplet from the solid surface. So you indeed decouple the droplet from that surface. Right. So one of the things that we did recently is to try to sort of come up with an idea or a simple way of characterizing what is the apparent wettability of liquids on top of these surfaces. And the idea is the following. So if you have a thin film of the lubricant and that thin film coats the droplet fully, then what you can come up with is a little toy model that tells you about the surface tensions at the level of the apparent contact line, so at the edge of the droplet. And if you do a simple force balance between the different surface tensions, then what you end up with is a new kind of equilibrium contact angle right? But it does not depend on the surface tension of the solid in contact with the liquid, because that interface doesn't play any role in this force balance, right? And the idea is that if you apply that simple theory and you compare that to the experiments, you find a very good agreement. So in a way, this is the key in order to understand all the wetting processes that occur on these surfaces, because you know the equivalent equilibrium quantity on those surfaces. Still have the ghost. Right. So what I'm going to talk about today in terms of these three applications is how we use these ideas in order to describe systems when we manipulate the droplets using these sort of boundaries. So I would like to start with a first project that I carried out with my first PhD student, which is also a graduate of the university, and that people in this department, particularly Rafael, were kind enough to sort of put me in contact with, but also Aurora. And this is Elfego, who is now has defended his thesis, and he's carried on to become a postdoc in the group. And his work was on the idea of manipulating droplets inside confined geometries, right? And the idea is the following. So if you have a droplet between these surfaces and you manipulate it, then you see that there is a very sort of smooth motion of the droplet. And one of the things that you notice right away is that the equilibrium or the static configuration of the droplet seems to have a very simple structure, and that is a truncated sphere. And this is what we call a liquid barrel. So you can actually do a very simple calculation in order to figure out that these indeed are equilibrium surfaces that satisfy boundary conditions imposed by the equilibrium contact angle of the liquid with the walls, but also depend on the geometry of the confinement, in this case, the tapering angle.
Excuse me, but in your previous slides, the droplet was causing the moving of the wall, or the wall
Right.
was moved externally?
So this is a plate which is moved externally, and then what you see here is the response of the droplet to that motion. Yes. So then, in a way, what you're doing is that you're manipulating the tapering angle of the confinement. Right. So we did some work on these surfaces, and the idea was to try to characterize what happens when you push the droplet out of equilibrium by changing the tapering angle or the equilibrium contact angle, and how these droplets relax back to equilibrium. And we call these configurations liquid barrels because they're different from other configurations that have a different topology. So for example, if you have a fully closed surface, then we call that a drop. And if you have contact with the wall, we call that an edge blob. And if you have full wetting, so that this is not an equilibrium configuration, but it will spread along the apex of the wedge, then we call that a capillary bridge, right? And all of those configurations will depend on the interplay between the tapering angle of the wedge and also the equilibrium contact angle of the droplet with the walls. So then the idea there was to sort of try to understand what is a more efficient way in order to move the droplet about based on these parameters, right? So what is more costly energetically? Is it more costly to change the wedge angle, or is it more costly to change the equilibrium contact angle? And you can find the answer by looking at these equilibrium configurations, by plotting, for example, the free energy of the droplet as a function of the equilibrium contact angle or the tapering angle of the wedge. And what you see is that when you vary these two parameters, say, for example, that I take my equilibrium contact angle and then I increase it so that my walls become more and more hydrophobic, then what I will see is that the droplet is moved progressively outwards from the apex of the wedge. So I'm changing the position of the droplet, which is what you see here. And you see that that comes at a cost in the surface free energy, and the reason is because you're increasing one of the surface tensions, right? But if you do the same thing by changing the tapering angle of the wedge, right, then what you see is that you can achieve the translation of the droplet along the confinement, but the energy stays exactly the same. And that's rather interesting because it implies that you don't have to do any conservative work in order to move the droplet along the constriction. And the reason for this is rather simple. It has to do with the fact that, as you're changing the tapering angle, in reality what you're doing is just moving the boundaries in the frame of reference of the center of the sphere, right, of this truncated sphere. And by doing that, you're not changing anything else. So you're not changing the contact areas or the equilibrium contact angle. So that means that these truncated sphere solutions are actually energy invariant solutions which do not change upon translations along these boundaries. And that's a rather nice idea that you can also apply to find, for example, equilibrium solutions for spherical shapes that are truncated by solid boundaries. So, for example, you could do the same thing to find the equilibrium shape, or to apply this to understand the equilibrium shape of a sessile droplet in contact with the boundary, but also to extend it to talk about spheres which intersect droplets which are in contact with planes, and also Pickering emulsions, which are emulsions which have particles which are embedded at the interfaces between the liquid and the gas. Right. So we wanted to do some experiments in order to actually give some meaning to this translational invariance, because of course whether you are in an adiabatic situation will depend on timescales, right? So how quickly your droplet is able to relax upon a displacement from equilibrium. And you can formulate that rather easily from a coarse grain point of view. By writing an equation such as this. So for example, if you look at the energy of the droplet, you will have a contribution for the rate of change of the energy of the droplet that comes from the free energy itself, but also from a conservative displacement from equilibrium, and also from dissipative losses, right? And you can rewrite this equation by choosing appropriate variables. So for example, if you think about a time scale of actuation of your droplet, right, then the total energy change upon that actuation will end up depending on this external time scale, but also on the internal time scale of the system, which will have to do with the spring constant of the conservative term and the friction term of the dissipative term. So that will give you a contribution to the total change in energy that will scale with the ratio of these two time scales. And what this tells you is that if you carry out your actuation over a long enough time scale so that your system is essentially always in equilibrium, then the total energy change will be negligible. Right. Okay, so the reason we wrote this simple model is because we wanted to characterize this experimentally. So what we did is that we carried out experiments where we take the droplet and then we sort of put it in a state which is out of equilibrium so that it wants to relax to an equilibrium position down the wedge. And from that you can observe the relaxation, which turns out to be exponential as you would expect. You can define a time scale, and the punchline of this is that your time scale ends up being something which is between 1 and 100 seconds, which tells you about the feasibility of using this approach in order to move droplets by actuating the boundaries at very little energy cost. So this is a route towards exploiting the low friction present in these systems in order to move your droplets without necessarily imposing an external force which is significant. Right. Okay. So that's the first topic that I want to tell you about. The second one is a very exciting topic for me from the point of view of doing something very interesting, but also with a collaboration that I established with Marc, and it took us 10 years to actually publish a paper together, so I'm very pleased about that. And this has to do with understanding what happens when you do evaporation on these sort of slippery surfaces, right? And the idea is that if you look at the evaporation on a flat surface, then the process is rather boring because you have very little friction. Then your droplet essentially is just a succession of equilibrium shapes up to a point where the droplet starts to see the length scale of the thin film underneath, and that is what leads to this sort of decay of the angle at long times, if you like. So that's not very interesting. What is interesting is to actually look at what happens when you introduce some kind of topographic constraint on your surface. And in this case, what we did was to study the effect of imposing a sinusoidal shape on the surface to see what happens to the droplet when it evaporates. And you have to wait a long time for this experiment, so you have very nervous PhD students sort of hoping that nobody comes into the room to sort of knock on their experiments because it will spoil it. But then what you see is that at the beginning nothing interesting happens, but then at some point then you see that kind of jump. And then if you wait a little bit more, then you see another one, which is going to happen just there. So what's going on there? So we did loads of tests in order to rule out that this was due to static friction on the surface. So I'm not going to show you those results because of time constraints. But the idea is that you can do some lattice Boltzmann simulations, and these are very nice results that AlphaGo produced with a code that he created himself. And what you see there is that initially everything is nice and quiet. What you see there is the pressure field, which is homogeneous inside the droplet. And then at some point, if you wait until the edges reach the troughs of the perturbation, then you see an out of equilibrium event where there is a pressure buildup that leads to the motion or the shift of the droplet. So these simulations are done with no gravity and with periodic boundary conditions along the transverse direction, so that allows you to rule out three-dimensional effects and also gravitational effects, right? And it allows you to find the solution to the problem, which is actually rather nice. What you have here is a bifurcation. Indeed, what happens is that if you start with your droplet at a peak of the perturbation, then that initial shape is stable. But what you find if you do the analysis is that there are two unstable branches which are sideways to those droplets. So these are asymmetric solutions which also exist. And then as you decrease the volume of the droplet, which in this case corresponds to the cross-sectional area, at some point these meet, and then that leads to a bifurcation, which in this case is an inverted pitchfork that leads to the translational motion of the droplet to the other stable branch, which in this case corresponds to a valley branch, right? So that's why the droplets shift. What's that? Well, in the simulations you have... Yes, so in the experiments you break the symmetry because there will be imperfections on the surface or there will be thermal fluctuations. In the simulations you have to introduce a small noise in order to break the symmetry. Yes, okay. And so the idea there is that you can do free energy a landscape in order to track those bifurcations, and that allows you to predict that there will be these hops between peaks and valleys configurations that lead to this succession of stable equilibrium states that become unstable at these bifurcation points. And you also find that this depends on the amplitude of the perturbation that you impose on the surface. So for low amplitudes, the bifurcation is still present, but the jumps are not so widely spaced. But as you increase the amplitude of the perturbation, what you find is that these states become more and more condensed. So it is very difficult to find the droplet at that particular positions in the surface. You find them only sort of constrained close to peaks or valleys. Right. So one of the things that we're working on right now in relation to this is to try to extend this to explore the design of surfaces that allow you to manipulate the droplet shape as it is evaporating. So for example, this is just a toy experiment that we did where we try an egg box shape. And what you see is that, again, there is a succession of two alternating shapes. We call this a diamond, and then we call this a rectangle. And then what you see is that that allows you to control the aspect ratio of the droplet as you're decreasing its volume by virtue of the evaporation process. Okay, right. So that's it for the evaporation on these wavy surfaces. And now I would finally like to talk briefly about something which we're working on at the moment, which is new and very exciting. And it has to do with the idea that, well, we have these droplets which are sitting on top of this layer of oil, right? And they are actually not seeing the solid, yeah? But if you introduce a topography in the solid surface, that allows you to shape the liquid layer, right? So it's a little bit like doing liquid on liquid wetting, where you are patterning the liquid surface by means of coupling it to an underlying solid that the droplet actually cannot see. And the first thing that we're looking at is how to exploit this in order to create the self-propulsion of droplets. And this is a topic that has been explored a number of times in the community. And essentially you have two different ways of moving droplets on top of a surface. You can impose an external driving, say for example by doing a mechanical actuation or a temperature gradient, but you could also do some passive intrinsic mechanism, and most of the time what you would do is to impose a wettability gradient. But the problem is that if you have a wettability gradient and there is direct contact between the droplet and the surface, then there will be some pinning effects, there will be some static friction, and that severely hampers the motion of these droplets. So then you only get motion over length scales which are comparable to the size of the droplet. So what we have tried now is to create a surface that has this sort of rail sort of structures, right? And then surprisingly what you find is that if you choose your fabrication method right and the liquid combinations right, then you can actually create a thin layer of the oil that decouples the droplet but still allows you to have this what we call in this structure surface jargon, superhydrophobic or Cassie-Baxter state, where you have this sort of fakir effect where the droplet is actually suspended on top of the posts. And the nice thing about this is that if you do a simple calculation in order to figure out what is going to be the apparent contact angle of the droplet on top of these surfaces, it turns out to be the apparent contact angle that you would expect based on the apparent contact angle calculated from the theory that I presented at the beginning. So this simple force balance that doesn't take into account the effect of the solid. So this is really liquid on liquid, apparent Cassie-Baxter state. Right. So what do we do with that? Well, Gabby, who is a postdoc in the lab, has created these very nice micro-pattern masks. Well, he varies the fraction of these rails along this longitudinal direction. And what you would expect is that because the droplet likes to be in contact with the oil, it moves to a region where there is a higher packing fraction of these rails, because that's where it will find a higher surface area covered with the oil. And then if you carry out the experiment, and that's what you see. So you see droplets moving over and over and over, well, for a long time and over long length scales. But you can also vary how quickly they move and for how long they move by choosing the gradient of wettability on the surface. So these droplets,
What's the difference between those?
so this has a high gradient in wettability and this has a low gradient in wettability. Yes. So the driving force here is higher than there. Yeah. And one of the interesting things about these surfaces is that unlike the equivalent superhydrophobic surfaces where there is very little contact between the droplet and the surface, here you have a meniscus which is formed by the thin layer of oil which is coupling the solid to the droplet, and that leads to this low lateral adhesion, so there is very little friction if you want to move in the direction parallel to the solid, but it creates a high normal adhesion, which means that this is a good way of, for example, catching droplets. So these are droplets that have been fired from the bottom and then they stick to the surface. As this is something that you would not be able to get away with if you were using a superhydrophobic surface where there is very little contact area. Okay, so with that, I would like to end. Well, I would like to say that there's a lot of things that we are doing in this regard. We're looking at measuring and modeling the pinning forces, the self-propulsion force, and the normal adhesion force, so we're making progress on that. And with that, I would like to thank collaborators. So people in Northumbria, PhD students such as Bethany, James, but also postdocs as Gabby and Elfego, of course, and then some visiting students, Yuan and Anthony from France, and then some other collaborators there in terms of experiments and theory. But then, of course, Marc for his contribution to the SNAP operation paper, and then Halim, who's working with us in Durham to do some theory on the self-propulsion of droplets. So thank you very much.
Very nice talk, Rodrigo. Questions? Mariano.
This is just a curiosity, Rodrigo. Can you make it move up?
So thank you for that question, right? So yes, you can move them up by doing an incline, but actually that is the way that we use in order to measure the pinning force. Because what happens is that the droplet moves up, then at some point, for a certain tilting angle, gravity wins, right? And then, but what we find is that it will stop there, but you still have to tilt it a little bit more in order to bring it down. And that gap allows you to measure the pinning force. And it turns out to be a very low pinning force. Yes.
More questions? Ulises?
Is it working? Okay. Thank you very much. I was wondering about the wettability. How do you quantify first the wettability? And if, when you put a gradient, what are the values of the wet? I mean, how high can this gradient of wettability be? Like how strong?
So the way we measure that is by looking at the change in the apparent contact angle at a local point on the surface. So if you have full wetting, then the contact angle would be 0. If you have complete non-wetting, it would be 180 degrees, right? So in this case, the surfaces have a reference contact angle, which is when you have a completely flat surface that has no patterning on it. It just has this layer, which is about 110 degrees. So that means that you can go from 110 to something like 160. which is the maximum contact angle that we have managed to achieve using the patterning. Yep.
So the gradient is like 40 degrees in?
So it's about a 40-degree gap in the contact angle, yes.
Okay.
Yeah.
And
But the thing is that because the friction is so low, right, the driving force that you get out of that, which has to do with the surface tension and the difference in the contact angles, is sufficient to overcome this static friction.
My final question is, how do you translate these 40 degrees into force? How big is this force?
So we have a way of measuring that, and the way we do that is by doing a force balance between the driving force and the resisting force. And you can also do that by using these measurements, including the effect of gravity. So the forces that we get are of the order of micronewtons.
Thank you.
Okay. More questions? I had a question about your different degrees of, can you put the transparency with your 5 degrees of?
5 degrees of, like that?
No, you told me there are different degrees of hydrophilicity or something like that, no? So in these 5?
In this part?
In the 5 that you put, stop the movie about that. It seemed to me that some of them go at the constant velocity roughly.
Yes.
And the one on top, it accelerates and then it stops. So can you explain that, please?
Yes, so that one is because at the beginning you have inertia, right? And then the system is completely out of equilibrium. Mm-hmm. At some point, static friction kicks in, but in the particular case of the top one, there is some fluff on the surface. So there is a defect that's spinning the droplet. Yes.
So it stopped because of the defect.
Because there is a defect, yes.
Okay.
Yeah. But then you see the bottom ones, right? They carry on moving, and that's because these are surfaces that do not have a defect. Yeah.
Okay, and in which line scale would this thing stop? Obviously, you don't have a perpetuum mobile, you know. So, no. On which scales would that stop? Like centimeters, meters, or do you have an estimation?
Yes. So for these surfaces, the maximum length that you would get is about 30 centimeters.
Okay.
Right? Now, but this is just a fabrication limitation. So the real threshold for arrest of motion has to do with when the driving force is balanced by the pinning force, right? So what we find is that for these surfaces, the pinning force is typically between 1/20th and 1/10th of the driving force for these surfaces. Mm-hmm. So that means that's why you can have a long range of motion. Yeah.
Okay, very nice. More questions?
More gradients to play about?
No, so far we have tried this geometry. It has to do with these rails, and the reason we did this is because by doing rails, you eliminate the sort of corners that you would get if you were to do posts, right? Yes, but you're right.
Electrowetting and things like that?
Yes, so that yes.
Yeah, because I saw that the last paper that you've got with Elpigo has to do with electrowetting, yeah?
That's right. So, but that's a slightly different project. But yes, so one of the future branches of this is to do electrowetting on these surfaces. Okay.
Yeah. Okay, I think we have to move to the next talk. So please, we thank Rodrigo again. And then I think the next talk is Rodolfo, no? Huh? Mariano, yeah. I wanted you to be the chair, Mariano.
I can chair myself, sure.
Yeah. Perdone, señor, ¿puedo la pueden cerrar? Es que si no empieza a cochinar, interrumpe al speaker, por favor. ¿Sí? Do you want to be the chair? I'm tired.
Yes.
Yes. So 25 minutes. Do you want my chronometer? Mira, aquí lo que ponen.
¿Nada más para esta sesión?
20, ¿eh?
¿Para esta o todo?
Solo para esta.
Ah, okay.
Le avisas a los 20 que le quedan 5.
Okay.
Y luego hay 5 de preguntas.
Ok. Ya empezamos. A los 20 le quedan 5 minutos.
Le aviso que a los 20 le quedan 5.
¿Se me oye ya? Déjame ver si lo apago. ¿Se oye? Okay.
Okay.
Well, okay. We are going to start with Mariano López de Haro from the Instituto de Energías Renovables in Temisco. Yes, Mariano.
Thank you. As you will see, there's a completely change of topic. I have the pleasure of having met
Aurora a long time ago, but I haven't had the pleasure to work with her directly. Indirectly, yes, through Eugenia and through Rafael, but not directly. However, I can witness the fact that she is a very, very knowledgeable person concerning eating places. And she really takes you. I remember that time we went to the market. What's the name of? La Boqueria in Barcelona. I remember that fish that you suggested. Anyway, so as you can see, we can share all sorts of things. And again, I wanted to talk today about the topic that started about 20 years ago. So you will see a story that I've been carrying out for 20 years, more or less, and that hopefully will continue. Maybe not for 20 more, but more so. And this has been done with in collaboration with Andrés Santos and Santos Barbo Yuste from Extremadura, who also asked me to congratulate you on your entering the academy. So the outline of my talk, I will give you a very, very brief refreshment of the previous work that both we and other people have done over here. Then why should I be speaking about hard hyperspheres and more mixtures of hard hyperspheres? Okay. And then I will go on to the technical details. I'll have to put a couple of slides with technical details, but don't worry. And then I'll exemplify the theoretical development for spheres in 5 dimensions, 5-dimensional hyperspheres, and then I'll conclude. So, previous work, as I said, I'm not lying, it's, oops, what have I done? 1999. And we produced a paper in which what we wanted to do was to have an equation of state for a fluid mixture that would be given in terms of the equation of state of the single fluid, okay? One component fluid, and then express that for a mixture in d dimensions. And then I managed, as I'm always mumbling around, I managed to convince some simulators to carry out the simulations in 4 and 5 dimensions. And to my knowledge, this was the first time that these simulations were carried out. They tell me I'm not a simulator, so I really don't know, that they are in a way more difficult than in 3 and 4 dimensions. Incidentally, I also persuaded some other people to compute virial coefficients in 4 and 5 dimensions, and I want to mention that one of them, Noé Almarza, is now, he passed away, but I also persuaded him to do that. I cannot do that, but I can produce some. You can persuade them. I can persuade them, yeah, I have persuaded many people over there, okay? Now, in 2008, we managed to, I didn't write most of it, the review of the things that we had done on the approximation that we had been using to get the equation of state of a mixture in d dimensions from the one component fluid. And very recently, comparatively speaking, Bishop and Whitlock, which are part of the community that is interested in hyperspheres, did Monte Carlo simulations. I must say that the molecular dynamic simulations that Alejandre and Minerva González Melchor performed under my suggestion were later confirmed by Monte Carlo simulations by Bishop and Whitlock. And then they used the same mixtures that we had done, and very recently they did more simulations on other mixtures. In the meantime, we have been developing a different approach that I will tell you about in a minute, of how to relate the equation of state of a d-dimensional mixture with the one component fluid. And that was in 2017, and that was exemplified in that paper by through the examination of 2-dimensional mixtures. Okay? Okay. Why had hyperspheres? Well, of course, everything is spherical, the spherical cow. So that's why we want to do that, both in and out of equilibrium. They are the simplest model of a many-body system made of interacting particles, and it's also important from the hard sphere model is also important from a practical point of view, especially at high temperatures and moderate and high densities. All the structural and thermodynamic properties are mainly governed by the repulsive forces, and hardcore fluids have been, for instance, used as reference fluids in thermodynamic perturbation theory. That's hard spheres. Hard hyperspheres are the natural extension of hard spheres to arbitrary spatial dimensions. Why should we want to go to more than 3 dimensions? Well, there are reasons. For instance, in other branches of physics, going to 4 dimensions or 4 plus epsilon dimensions may be advantageous to do renormalization group calculations. But over here, if you increase the dimensionality, it has been proved that the phenomenology that is shared by these systems, namely phase transitions, occur at the smaller density. And therefore, in some instances, in fact, in the infinite dimension limit, they become amenable to exact results. So that's why they are interesting, okay? That's what I said. And you can study both static and dynamic properties, and they have been used for glasses, granular matter, colloids, etc., etc., etc. And of course, dealing with mixtures is in principle more difficult than dealing with single component fluids, and the literature on these systems is rather scarce. And as I said, I think we can claim, well, I cannot, but Jose Alejandre and Minerva González Melchor can claim that the first simulation on these systems was done in Mexico, okay? So that's why. Now, what's the system? The system is a mixture of hard spheres in D dimensions, additive hard spheres, which means that when they, when two particles of different species are in contact, the distance between their centers is the semi-sum of the distances of their diameters, okay? Now, that's just a few nomenclature. That's the number density. Oops. I don't know what I did. Now I don't know what I did. And never mind. Can you see the lines? If not, okay, never mind. I said, I have to define some quantities, which is the mole fraction, the number density, the mole fraction, the moment of the diameter distribution. I can handle both polydisperse and bidisperse or multi-component mixtures. So this moment can be either a sum or an integral. And if I take the a volume of a d-dimensional sphere of unit diameter, then it involves the gamma function. And that's it. Me lo puedes poner grandote, pero no sé qué hice. Okay? Okay.
No será esta.
Okay. Now, packing fraction. The packing fraction in 2, 3, or n dimensions is given by that, which that involves the moment of the d of the dimensionality, and that's the volume of the sphere. And these are the contact values. And if you express the compressibility factor of the mixture, you can express it in this way. That's the virial expression of. But you don't have the contact values of the radial distribution functions. So the first idea that we used in 1999 was to model these contact values. Okay? That's the simplest thing to do. And so we assume that both this multi-component and the single component fluid are evaluated at the same packing fraction, and that the dependence on these contact values on the sets of the diameters and compositions is just through this parameter, okay? And that's a universal function. And then we assume the simplest form. If this is universal, we assume that it's either linear or a polynomial or whatever. So I'll just stick to the two forms that we used. One of them is the linear form, and forget about the thing. What I want to point out is that you have something here which is important. That's the volume fraction of a single component fluid. That's exclude volume, sorry, of a single component fluid. And that's the way you can write the equation of a state of the mixture in terms of the one of the single component fluid. if you take a quadratic form, then you end up with something more complicated, whose form is in terms of the moments, but I won't go into that. And with that, with those approximations, now you have all the problems solved. If you give me the equation of state of a single component fluid in any dimension, I give you the corresponding equation of state of the mixture in any dimension. That's the idea. So that we proved, and we tested that in 2001, and it worked. However, there's a more, I would say, thermodynamic route to get the same sort of idea. That's to make an assumption on the free energy of the system, okay? Now, we assume that we express the compressibility fraction, the compressibility factor of the mixture at a different density than the one of the single component fluid. And we just equate the, actually what we normally do is not the compressibility factor, but the free energy of the mixture in terms of the free energy of the one component system. You end up with something of this sort, which is rather simple. Here's this factor again, that's excluded volume. And there's a couple of parameters. That's the effective packing fraction, and that's an alpha, okay? And this is the relation between the effective packing fraction of the one component fluid and the packing fraction of the mixture, and there's another parameter. So there's two parameters. How do you fix those parameters? You do an expansion and force this form to give you the right second and third virial coefficients. That's the two conditions. And then if you do that, those are the expressions. They are not very important. The important thing is that everything is fixed, and so you know exactly what you have to do to get the equation of the mixture once you have the one of the one component fluid. Of course, the equation of the one component fluid is not known in general either. So what do we do? Well, for 5-dimensional systems, there is a very good approximation given by Lubin and Michels, I think, yes. And it was in the 90s. I don't remember exactly the date. But they produced something that adjusted the simulation data then for a one-component fluid with this function. Those quantities are virial coefficients of the single component fluid, and those are well known. I mean, those are numbers. And here are the numbers, if you want to see them. And this function is just a fit, okay? That's the closed packing fraction, and that's also known. Here it is. There it is. Okay, so now the scheme is complete. How does it perform? Well, first we have to choose the systems, okay? So the systems we chose were the ones that were simulated in 2016. Those are the systems. X2 refers to the mole fraction of the smaller species, okay? That's sigma 2 over sigma 1, so x2 corresponds to component 2. And those are the ratios of diameters that they used, and those are the packing fractions. As you can see, these two are very similar, except that this, that's essentially equimolar, and these two differ only in their size ratio, which is relatively moderate, it's 2 to 1, okay? And this other two is the same sort of thing, except that there is an excess of small particles and very little of the big ones, okay? That's almost 0.98, okay? So, if anything of what I said makes any sense, you can work backwards. Assume that I give you data from this unpacking fraction. I give you this recipe. I give you these numbers. And then I ask, what should this look like? Okay? If everything I've said makes any sense, then you should get a universal curve. There it is. The points are the data from the mixtures. Those are the simulation data. And the line is just the Lubin-Michels semi-empirical expression. So this seems to be working. I mean, we started with the data from the mixtures, and we got the equation of state of the single component fluid that had already been tested against simulation data of the single component fluid. So it seems to be working. Now, how does it look the other way around. It will be no surprise that it does exactly what I'm saying. Over here, I haven't tested the other two approximations, what I call the zeta E1 and zeta E2, because they had already been tested. And the approximation is not as good as this one, but it's also very good, okay? But now, let's work, as I said, I promise you, I have a very good equation of state for the single component fluid. How good is it for the mixture? Well, there it is. I'm sorry about the quality of the figures. You cannot see, but there's 3 lines for the blue, 3 lines for the red over here, 3 lines over here, 3 lines over here. And you cannot almost distinguish the difference, okay? So you can say all of them are very good. But which one is the best one? Can you rate them? Well, of course, it's a matter of how you present the data. As they were saying, data is everything in our life, so I'll have to use the data in a much more clever way. There it is. Now I am doing the percentage deviation. And the 2 curves correspond. Blue is one of the, I don't remember which one of the, is the mixture B, and the other one's mixture 1. And that's, those 2 curves correspond to the E1 approximation, those 2 correspond to the E2 approximation, and those 2 correspond to what I call the SP, which is surplus, for surplus pressure or surplus free energy, okay? And if you take the other 2 mixtures, of course, this is E1, this is SP, this is S2, for, that's the mixture D, that's this one, and mixture C, which is the worst of the 4 of them in terms of our prediction, also gives you, this is E1, this is SP, and this is E2. As you can see over here, it's 2% more or less deviation. Over here is much smaller, okay? Much smaller. But the worst is always E2, which is surprising because you're approximating a function by a quadratic polynomial. You should expect that it would be better than the linear one, but it's not. Anyway, that's life. So, how am I doing? I've been very fast. Okay?
10 minutes.
No, you have 7 more minutes.
Okay, no, I'll be finishing very, very soon. Okay? So, I'll conclude.
That's good. We gain time.
Okay, I'm gaining time. No, but actually, I could say more things about the technical details, but I don't want to go into the details. What I say is that why is it that the new approximation works better than either the other 2? There's one thing that happens in 3 dimensions that doesn't happen in 5 dimensions. In 3 dimensions, both these 2 yield the exact third virial coefficient. Same as this one, because this is by construction. It has to yield the third virial coefficient of the mixture exactly. But in 5 dimensions, these 2 do not yield the exact fifth virial coefficient, third virial coefficient. Okay? So that's a clue. Probably that's part of the story.
Why 5 dimensions?
Sorry?
Why 5 dimensions?
Why 5 dimensions?
What's wrong or good about 5?
The fact that there are simulation data. That's all.
Has nothing to do with standard model.
No. Although I mentioned renormalization and all of that, that has nothing to do. It has to do with the fact that the simulations, the most recent simulation data, are for 5 dimensions, okay? There are some others for 4 dimensions that I'm not presenting here that we've also tested, but it's the story is just about the same, okay? Except that in 4 dimensions, the one single component equation doesn't work as well as this one, okay? But that's a technical issue. But is that all? Well, maybe the thing that we start in this new approach with the free energy has also more to do. Because in the earlier study, what we did was just to approximate the contact value. And that's a simpler approximation to perform, but also has less of a physical background to support it, okay? When you do the approximation at the level of the free energy and you use density functional theory to set some limits and some consistency conditions, then you end up with a new approximation. And that's probably, it's more consistent thermodynamically than the other one. And the good thing is that this simple linear approximation still keeps working pretty well. I mean, 2% is not bad, okay? 2% difference is not bad at all. But anyway, and let me say, I think I've got something. Yes, okay. Well, as I said, if you go to higher dimensions, you can lower the phenomenology to a lower density. Therefore, for instance, freezing would occur earlier in 5 dimensions than it would in 3, okay? If you get freezing. So you could study that. Of course, the simulations are nowhere near, and we didn't go into that region. We know that in 4 dimensions, some of the mixtures that were examined in 2001 started to show some crystallization. This doesn't show over here because we haven't gone that far in the simulations. You didn't notice the density, but the density was rather small in those instances. Nevertheless, since it works for 2, 3, 4, and 5, well, the hope is that it will also work for higher dimensions. And mind you, if it's an infinite dimensional system, it will only give contributions up to the second virial coefficient, and that's exact. So one could go on and on and on and carry out this program for the next 20 years, okay? And on that, thank you very much. That's it. And I did it in 25.
Well, we have a lot of time for questions. Yeah?
Ulises?
No? Ulises? Eugenia?
Well, yeah, I mean, it's strange, you know, like, why do we want 4 or 5 dimensions? Normally in StatMech, you want, like, the upper critical dimension because it's the dimension in which mean field works. But
right.
Other than that, I mean,
that's
why
infinite.
would you like to work in that? I mean, you're not doing string theory or something. So I think you have to give us some arguments to convince us of why is that important.
No, I will tell you why it's important.
But
go ahead.
Him that. Let him defend.
No, I just tell you what Lord Kelvin said about physics. He said physics is nothing else but finding the equation of the state of your system.
That's right.
And his system is 5 dimensions. What's wrong with that?
She doesn't like it. She wants 3 or 2 dimensions.
No, I mean, I just think that, I mean, we are in the 21st century. You need arguments to, like, earth your research. No, I mean, of course, we can do sophisticated games, and it's very valuable and very complicated. I'm not saying there is no merit in the solution, but how do you justify doing that? Or why not 27? Or why not 9? I mean, I would like to have an argument.
I tried to give you an argument earlier on, but I'll insist on that. Yeah. If you go to a higher dimension, and these systems, all hardcore systems, share the property of having a solid fluid transition, okay? In 2 dimensions, as we were discussing earlier, that's difficult because that goes through a hexatic phase and then it goes to a solid phase, okay? And it's not understood as yet. The hope is that by going to higher dimensions, you will be able to understand problems such as the glass transition, granular matter, things that happen over there. It's not what I do. If you have the equation of state, as Rafael was pointing out, then you're in a better shape to study those problems. What I wanted to prove is that my equation of state is reasonable enough within the knowledge of the simulation data. To use it further, I invite you to join that group. Okay?
Okay. Go, please.
I think my question is related. Do you want the mic? When I was doing, in the old days, when I was working on 4 minus epsilon expansion in renormalization group calculations, at the end of the calculation, I set epsilon equal to 1, so that I go back to 3 dimensions. I make some prediction of critical exponents. So I want to, even though you do 4 minus epsilon, but in the end, we predict something at 3 dimensions. So now, in these higher dimensional studies of equation state, are there things that you can say to 3 dimensions by learning at 5 dimensions? So that's the question that I'd like to know.
It's
possible?
There's one transition, which is a liquid-liquid transition in 3-dimensional mixtures. That's not fully understood. The reason being that maybe when you got the mixtures, this is preempted by a solid transition of the bigger spheres, okay? The hope is that either by adding some polydispersity to the mixture or by increasing the dimension, you can get it to a lower density where you can study that, okay? That's the hope. It's not the realization, it's just the hope. Therefore, the insistence of deriving equations of state that would help you, say 5 dimensions to go back to 3, then it would be useful.
No, I know sometimes we do 4 dimensions to study across the crystals.
That's right, that's right.
Things like that. So, but you want to go back to lower dimensions so that measurement.
Of course, of course. Ulises?
Thank you. Do you think this result gives us a perspective? Because we know, as you said, the analytical result for infinite dimensions. Do you know this gives us a perspective? How many dimensions will be close to infinite? Like 50, 100, 200?
No, I think, as far as I know, the only theoretical studies that have been carried on so far go up to 9 dimensions, okay? And there's a reason also for that. In the one component case, the Perkus-Jevic equation, which is the usual approximation in liquid state theory, only is analytical up to 7 dimensions, okay? Otherwise, you have to recur to numerical solutions of the equations. And going beyond that, I think you have to do it by computer. But again, as you add the dimensions, you have to think of hypercubes and things like that. As I say, I'm no simulator, but I think it's going to be difficult. I think. Maybe I'm wrong. Therefore, 10 is more than enough. 10 is almost infinite, okay? So if you are able to get some idea of the phenomenology associated to these fluid transitions by going up in dimension and then examining what happens, then you may be able to separate the metastable transition from the stable one and then study that. That's the hope. I'm not saying that we're going to do that, okay?
Rafael?
Thank you, Rafael.
One more question? Okay. Okay.
We can talk later.
So thank you very much, Mariano.
Okay. Tienes que poner la tuya, pero no sé, ¿está todo en orden? Ay, déjame que me quite esto porque no... ya.
Sí, nada.
Tengo que enchufar aquí. A ver, Alberto, ya te puedes llevar la máquina porque él va a utilizar la suya. Ya está, espera.
Okay, the next talk is by Rodolfo Cuerno from the Universidad Carlos III de Madrid. And well, the title is here, and I will advise you after 20 minutes.
Okay, good. Thank you. So let me start by thanking very warmly the organizers, Eugenia, Rafael, for the kind invitation to join this celebration of the inception. I learned this word today of Aurora Hernández Machado as a corresponding member of the Mexican Academy of Sciences. In my talk, I will be describing some work actually I've been doing ever since, maybe for the last 25 years. Thank you. Which have been around the effect of fluctuations, the relevance of fluctuations on interface behavior, especially at micron scales or length scales below a micron. Let me start, of course, every motivation is personal. Let me start with mine. This actually dates back to my time as a postdoc, when I started working on a surface modification technique that is called ion beam sputtering, by which one shines energetic ions onto solid targets, eroding material out of the surface and leading to formation of self-organized patterns. Actually, I have to say that it is this technique in which I'm still involved, which brought me in a previous, relatively recent visit here to work with in Instituto de Física with a group of Dr. Ricards. Actually, these were 10 years, more or less, after the invention of the atomic force microscope. So the quality of the image is not that great, but what we can see is the formation of a periodic ripple pattern on top of a silicon oxide film, which is being irradiated by xenon ions. We see the ripples. This system is very far from equilibrium, so there are many defects being produced on the structure. To such an extent that actually, if we zoom out and we lose resolution, space resolution, let's say by a factor of 10, eventually there's no trace of the ripple pattern. So in a way, this is a bottom-up, we could say, relevance of fluctuations in the sense that they really modify the behavior of the system. And this is actually an example of spatially extended systems subject to very strong fluctuations for which the hydrodynamic, let's say, large-scale behavior can be quite non-trivial. Of course, there's another complementary, I would say, way to think of the importance of fluctuations, and we can take this very well-known example of a solidification process by which a snowflake is formed. So we could consider how, let's say, relatively simple approaches to model this system have to be modified in order to account for the fine structure that can be seen here of these dendrites, which today we know has a lot to do with thermal fluctuations. So this is a very natural pathway in order to increase the predictive power of our models when we go to smaller and smaller scales. So actually, to give some background on this, the start of my story today actually corresponds to what in Pisman's story on pattern formation and nonlinear science history corresponds to a back to specifics trend. So trying to search for novel at the time, these are the 90s, context for pattern formation and nonlinear phenomena. And this is, for instance, nanostructure, one such case, even though pattern formation, let's say, in crystal growth systems and in hard condensed matter has a very longer history than this. It dates back probably to the studies by Frenkel and others, and Frank, in the 30s on crystal growth, and not very far from, let's say, classic approaches, more focused on macroscopic systems such as fluid dynamics, Rayleigh-Benard experiments, and so forth. So the context for the examples I'll be discussing in this talk correspond to the dynamics of actually surfaces and interfaces as physical systems. Of course, these systems become more important when we go to smaller and smaller scales, because the surface to volume ratio becomes more favorable. Many times these systems are under growth or, let's say, erosion conditions, and it's usually the case that growth events take place right at the interface, which provides, by the way, the locus for the exchange of energy and matter between the system and the environment. So, and today, okay, and this is a well-known scales diagram, where we can see that from distances to atomistic to, let's say, a few microns. Another very interesting issue is that the frontier between inanimate and living matter becomes to some extent blurred, and many phenomena can be found in both realms of condensed matter physics. So as scientific issues, coming back to the first two slides, one of them I'll be considering is the asymptotic behavior of systems which are spatially extended and subject to strong fluctuations. Historically, a very important role in the understanding, theoretical understanding of this topic has been played by critical dynamics, in which we have the dynamics of, let's say, a order parameter, scalar order parameter that is evolving subject to fluctuations that can correspond to thermal or otherwise, fluctuations of a different origin. And there's the complementary view that I was mentioning about the relevance of noise for macroscopic systems when we try to make our descriptions as accurate as possible when we go down in physical scales. In all this story, of course, and this has been discussed in a number of presentations today, a very important player has been phase field formulations, in which, to some extent, one couples an order parameter to physical fields. One can even enhance these dynamics by the addition of suitable noise terms, and eventually tackle the description of relatively or even highly non-trivial morphologies in the context of this talk, such as those produced, for instance, in electrochemical deposition. Okay, to some extent, the idea of the talk is that Aurora and myself have been playing this or investigating the role of fluctuations, simplifying matters strongly in opposite directions. So while Aurora was starting, like in these very nice experiments, considering macroscopic fluids and how some type of noise, in this case quench noise, affects the system evolution. In my personal case, I was starting, let's say, from the more microscopic world and seeing how fluctuations control or not the asymptotic behavior of the system. As is well known, okay, this is a Hilly-Shaw cell. We have these obstacles that decrease locally the gap, and we can see that when the fluid reaches them, it moves faster. And okay, the size of these obstacles is macroscopic, and it of course leads to a very much complex imbibition dynamics than in the absence of these quench noise sources. So one has to resort to statistical description of the process that typically makes use of observables such as the roughness or the root mean square deviation of the surface height, the mean, the front position around the mean value that evolves non-trivially in time, And we can also study correlations, let's say, in Fourier space through the high power spectral density. As you see, very frequently, this behavior leads to power law behavior with non-trivial exponents that relate somehow to classical critical dynamics, but introduce strong novelties. More or less simultaneously, this is one example of our work. This corresponds to experiments on the ion beam sputtering technique I was mentioning before. And as you see in the power spectral density, there's a very well-defined peak that corresponds to formation of a very characteristic pattern. But if we consider longer and longer irradiation times, what we see is that the disorder kicks in, and actually power laws are established also in the behavior of the structure factor, telling us that the macroscopic behavior is controlled by fluctuations. These are the experimental pattern corresponding to the previous power spectral density, and we've, along the years, been doing modeling of these systems through, for instance, single field evolution equations like this, with or without noise. In this case, this is the celebrated Kuramoto-Sivashinsky equation, and variations around this model seem to be able to account for these experiments with relative accuracy. So more or less, this is the situation around the 11th Física Estadística FISES meeting. As many members of this audience probably know, there's a long series now of conferences every 2.5 years, more or less, for the Spanish community on statistical physics and nonlinear science. The series started already more than 30 years ago, and of course we have met before a number of times, but the interaction and overlapping interest with Aurora was increasing with time, and I would say it reached an interesting peak around this time. I was digging, trying to find, and I did find the group photo. I was unable to locate myself here, so if you find me, please tell me. I'm not really sure, but I do think Aurora is somewhere here. I think it's more clear. Okay, I think we all know the interest of Aurora in everything cultural, and then it's easier to spot her here. This was a very nice tour we had around the Roman walls in Tarragona, which I really recommend. And actually, the guide explanation, and Aurora is paying close attention to it, was really very, very interesting. Sorry? Yeah, but okay. The royal family in Spain does these things, but okay, I just didn't. Okay, actually, the involvement of Aurora in the physics, statistical physics community in Spain has been very strong, and is fortunately still, and in future will, for sure, will be. And okay, she's been acting, for instance, as a member of the scientific committee for a number of editions, and playing really a leading role in the community. So we are in year around 2003, when we submitted our first application for a grant proposal that was eventually funded by the Spanish Ministry of Education, I think it was at the time. This has changed very dynamically, and this is the continuing grant. Okay, you can probably identify numbers of the audience in this picture, plus some additional colleagues and friends. This was the kickoff, as I say, of the continuing grant from 2007 to 2009. Sorry?
There are many, Rodrigo,
Many. Yes, and okay. This will be the usual suspects for some additional photos. What did I do? So, in the context of this particular grant, we finally got some, that our approaches and interests really overlapped, and we're doing some collaborating work also together with Mario Castro, with Aurora, and it was in the context of epitaxial growth, which is like nanoscale, and using the phase field technique that Aurora has been applying so successfully to so many realms of condensed matter. This is a theoretical cartoon of a molecular beam epitaxy chamber where molecular species are shown onto a target, and then if this crystal happens to be slightly miscut around a high symmetry plane, then the steps are formed, and then there's a, okay, these are very nicely illustrated in this STM image by Max Lagali's group. And because we have an external flux of adatoms, well, there's a very non-trivial dynamics of the steps. And of course, dynamical theories are required in order to fully understand the eventual morphology of this thin film that in principle should be as flat as possible. There is actually a classic model of this where one models the concentration field for adatoms on each terrace, and then the steps act as sinks or sources of adatoms. And we have all these equations coupled together. This is a highly nonlinear moving boundary problem that can eventually be simplified through a much simpler phase field modeling that eventually led us to reproduce some non-trivial step dynamics. As is well known, Aurora has and is playing a leading role in the application of phase field descriptions to a host of different physical systems. And this is a group photo from a workshop that took place, she was co-organizer of, in Dresden back in 2008, more or less contemporary to our work in epitaxy. Then there came a third grant together. Actually, I have to say that the grant group, a total of 5 different groups throughout Spain, Aurora's and ours in Universidad Carlos III were 2 of them. There were 3 additional ones, and these range up to 2012. This corresponds to the kickoff meeting of the third grant. And around in the context of that grant, I could like mention some work done by Aurora and collaborators on a still smaller length scale. So we have a fluid advancing within a microchannel, which is hydrophobic. Actually, this same work was mentioned in another presentation earlier this morning. And because of the Fakir state that takes place in the boundaries of the microchannel, for sufficiently low pressure differences, motion advances in a jerky way with avalanches. And actually, okay, this is the comparison between the experimental and phase field results. And okay, focusing on the average velocity of the front, the behavior is rather strongly fluctuating for small pressure differences, so to the extreme that the statistics of the fluctuations in the velocity field are not Gaussian, but correspond to one of these very universal families of extreme events distributions. In this case, the one of Bramble et al. And Gumbel-like distribution. And these are corresponding results for the phase field modeling. Contemporary to these works, we were also studying a different type of extremal statistics, but in this case was the effect of microscopic noise in macroscopic fronts. The fronts in this case correspond to those taking place in the Fisher-Kolmogorov equation, enhanced by the suitable noise term here. As we can see, there's a stable phase that is invading a metastable phase. We are co-moving with the advancing front that we can see is developing some long wavelength corrugations, but then can be traced back in detail to the microscopic fluctuations that actually are taking place at this leading edge here. And actually they correspond to what's known as the Carnot-Parisi-Sang universality class in one dimension. And doing a similar statistical analysis to the one I was presenting earlier, for the surface structure factor as a function of wave vector and time, and for the roughness. Okay, the critical exponents governing these fluctuations were identified to correspond to the KPZ equation, but not only that, as is well known, as has been clarified in the last, let's say, 9 years, after the exact solutions for the KPZ equation in one dimension, also the statistics of the height, the so-called one-point function, are also universal. And actually they correspond to a very important distribution, which is far from Gaussian, is strongly skewed. It has also non-trivial kurtosis that it carries the name of Tracy and Whedon, and it was in principle discovered in mathematical physics, studying random matrix theory, but today is known to provide some sort of unification for the fluctuations of strongly fluctuating low-dimensional systems, of which, let's say, the KPZ equation and kinetic Grafenin growth is just one example. There are additional ones found in many different contexts of mathematics and of physics and technology, I would say. Okay, more or less about this time. This is still another, thank you, another workshop organized by Aurora, and you can try to find the usual aspects and how many of us repeat. And I'll just very briefly flash some later developments, still going into smaller and smaller scales. This is more recent work by Aurora and collaborators, in which there's a polymer colloid mixture that is invading, like a less viscous one invading a more viscous one. And actually you can see like a Safman-Taylor finger evolving here, not the very small scales, and the conditions correspond to so-called super confinement, by which the typical scales for fluid flow compete or are basically similar to those of the container. Eventually, this can be engineered so as to produce regular droplet formation and so on. And this is the modeling where the Navier-Stokes equations that were also shown this morning are coupled to a concentration field, so that one can study in detail the velocity, pressure, and other fields. And actually, similar in spirit to this approach, I can tell you we are, and this is our latest work on the initial ion beam sputtering technique I was mentioning before. We are describing this nanoscopic system where, notice the scale is really nanometers, but the time is really macroscopic. This is one of the challenges of deriving accurate models for this phenomenon. Okay, in this case, we simplified into Stokes flow that actually similar to or analogous to the previous example we saw, allow us to probe the pressure and velocity fields within the amorphized layer. And even though some quantitative differences remain in terms of scales, many qualitative features are very similar to those found in experiments. These more recent works were discussed in a relatively recent workshop in Lausanne. And okay, don't you think that the interaction between Aurora and myself has reduced to workshops and grants? Fortunately, it has gone well beyond that to, I would say, all aspects of life, and I feel very lucky to have been, have enjoyed that type of interaction. Okay, you see all types of activities, and if I were hard pressed to choose one, I can tell you it's really, Aurora has been pioneering, as I say, many aspects, and one which is in particular, and I mentioned the physics community particularly valued in that context, is how to survive, in particular when you go to workshops and, and other kinds of activities. And with this, okay, I would like really to congratulate you on Aurora, and thank you all for your attention.
Thank you very much. Okay.
I may have misunderstood your statement about this one-dimensional exact solution of the KPZ equation.
Yes.
That's in a strong coupling limit?
Yes.
It's 1 plus 1?
It has been solved in the thermodynamic limit analytically.
Analytically?
Yes.
I see. I didn't follow this. I thought we had a lot of trouble in renormalization group analysis.
That's right. So,
okay, that's very exciting then. That strong coupling critical, I don't know, strong coupling fixed point is completely understood now then.
In one dimension, yes, because
1 plus 1, right? One time,
plus one
one
dimension.
space. Okay,
Yeah.
1 plus 1.
Okay, 1 plus 1 in terms of, well, one space
right.
dimension, one time dimension.
Uh-huh.
So there have been a number really of breakthroughs which have been mathematical tours de force,
I see. Okay.
starting, I would say, in year 2010.
Okay, I completely missed this literature, so this is very exciting. So what is the exponent z in that 1 plus 1 exact solution?
It's 3 halves.
It is 3 halves.
That's the one which we knew from the
We
very
knew long
early-
time ago from that. Okay.
Ever since, basically, the KPZ paper itself.
That's right, because by
That was
scaling you get that already.
Yeah.
So they didn't change that. Okay.
No, but
Very interesting.
What's
Okay.
really
Yeah.
quite remarkable
Yeah.
is that
Okay.
the exact solutions provide the probability distribution function for the local fluctuations of the height around the mean value. And that happens to be one of these Tracy-Widom distributions, which depends, the Tracy-Widom is a family of distributions, and which one takes place depends on global constraints on the system, such as if the total system size increases with time, as when you grow KPZ with a circular symmetry, or is fixed, as happens with periodic boundary conditions.
I see. Thank you very much. I have to find this literature. Okay, thanks.
That's good. More questions, comments? Gerardo.
Which context was derived this Kuramoto equation that you show?
Okay, we derived it. It has been derived in many different contexts. Actually, we were discussing with Marc last night. As far as I'm aware of, the first there are 2 candidates which are neither Kuramoto nor Shevashinsky to have been the first to derive the equation. And in each case, which are Homsi and Nepomniachtchi, 2 Russian physicists. In both cases, the equation was derived for a thin film falling down an inclined plane. Then Kuramoto derived it in the context of chemical turbulence, Shevashinsky in the context of combustion, and also turbulent systems, and there have been many other. And then in our case, we derived it from a physical model of ion beam sputtering. So it's this so-called weakly nonlinear, maybe Marc will mention some of this in his talk later. Let's say these equations with low order nonlinearities happen to be very generic, very universal. Maybe they have the universality of Taylor expansions somehow, right? To sufficiently low order, but yeah, they appear in many different places.
Yeah,
We have another question coming.
So in your project about nanofluids,
Yes.
were you always observing the same wavelength on this movie that you were showing, or the separation?
In principle, there's where was I? There's little.
This one here, the one here, and there was another movie before that one.
Oops, sorry. Which one you mean? Sorry.
That
This one?
Yeah, this one here.
So there's linear instability, and once at this stage these are nonlinear structures, and the wavelength is pretty much fixed. It doesn't evolve much with time.
Okay. More questions, comments? If not, well, thank you again for your talk. Okay.
So we now go for a 15-minute break.
Okay. So we have.
At 12 to 5. Okay.
Gracias.
hablaré de casi lo mismo.
Ah, vale, pues mira. Te he hecho un poco de publicidad.
Distintos problemas, pero dentro del mismo tópico.
Yo creo que...
No, pero he preguntado
Sí.
sobre, por ejemplo, la distancia entre los picos o estos.
Se mantiene en el tiempo. No lo hemos mirado
para tamaños pequeños.
Ya ves que sí, de momento, bueno, los tamaños mayores son en simulaciones como esta.
Es que esto es periódico, ¿no? ¿Esto?
Es periódico, sí. Sí, sí.
Claro,
Sí, sí.
Aquí será...
Javi tiene...
¿Cuál es la condición inicial? ¿Plano?
Es ligeramente perturbado.
Bueno, en una sinusoide.
Una sinusoide.
Bueno, la sinusoide que...
Bueno, no, es aleatorio.
Ah, porque después el diseñador, bueno, ya lo verás ahora.
Ajá.
¿Está abierto ya? Sí. Ah, no sé. ¿Quién es el chair?
No sé.
Puede ser el chair. El Rodrigo. Al Rodrigo que lo haga. Es tu cachondeo esto. Qué poco raro. Es que... ¿Alguien controla el tiempo? ¿El tiempo lo controla alguien? ¿A las 20? No, ¿cuándo se acaba? ¿25 es? ¿Cómo lo... Ah, pues como a las 20... Ah, a las 20 me avisas, a ver cómo voy.
All right, so let's... All right, so let's begin our session. So first talk will be given by Marc and complex behavior of interfacial flow. Let's thank our speaker.
Thank you. My name is, good evening everyone. My name is Marc Pradas. And, one sec. Yeah. So I'm coming from the Open University, which is in the United Kingdom. But my research journey started when I was a PhD student of Aurora. So I'm very, very happy to be here today to participate in this workshop and to congratulate Aurora on her membership in the Mexican Academy of Science. I also like to thank the organizers for inviting me to participate here, Rafael and Eugenia. And well, the idea of this talk is I'm going to give you an overview of the different topics I've been working. Particularly, I'll give you a summary of the work I did when I was a PhD student with Aurora. And then I'm going to show you some work that I have done more recently when I moved to the UK. So as you can see, the title is quite general, complex behavior of interfacial flows. And the idea when we talk about interfacial flows, what I'm going to be referring to, it's problems that are being drawn from fluid mechanics systems. So we'll be dealing mainly with liquid-gas interfaces and things that you can find in wetting phenomena, microfluidics, or interfacial instabilities. And typically, because of a variety of different reasons, these systems may exhibit the emergence of complex phenomena, such as, for example, chaotic motion, or if the system is affected by heterogeneities and additional or additive noise, this you might observe stochastic motion. So as you can see, my research interests have always been on the interface between fluid mechanics and statistical physics, and this is something I learned from Aurora. We have learned today, we have seen that Aurora has a huge and broad range of interest. She has been working on many different topics in biophysics, fluids, microfluidics, statistical physics. I never worked on biophysics. I always kept working on fluid mechanics and statistical physics. And the reason of this is because the first problem that Aurora gave me as a PhD student was a problem that involved knowledge of fluid mechanics and statistical physics. And that's the problem of a fluid flow in porous medium, something that is also known as imbibition in disordered media, so, very common in daily life experiences. If you put a piece of paper in contact with liquid, you will see that the liquid invades the paper. So the paper is an example of a disordered medium, it's a porous material. And the reason why this happens is because it's a wetting hydrophilic system, so the liquid wants to wet the material. Although this is a very simple experiment that you can do in your coffee break, this actually has received and is still receiving a lot of attention from different point of views. Of course, from engineering in all recovery processes, but from a statistical physics point of view, that's the one that we were interested in. This is very interesting because this is an example of surface growth, which we have seen a lot of examples in Rodolfo's talk about this. And the idea is that this is an example of where the interface undergoes what is called a kinetic roughening process, which means that the interface develops long-range spatiotemporal correlations. And as a consequence of these correlations, you observe a scale invariance on the morphology of the interface, and also interesting dynamics in terms of intermittency and avalanche motion. And I will show you some examples in the next slide about this. So this is from a statistical physics point of view, but also from a mathematics point of view, it's very interesting because this is an example of a multi-scale system. So the physics of this problem happens at the microscopic pore level, where the fluid is flowing through. But here we're interested on a macroscopic length scale, where we are really not interested in the microscopic details of what's happening inside the pores. So to bridge these two competing length scales, which are very separate from each other, one needs to use homogenization theories or averaging procedures, which in this example gives rise to this well-known Darcy's law equation, which takes into account this quenched noise term here that models the random capillarity of this porous material. So this is a two-dimensional system where we have averaged basically the perpendicular direction of this system. So this is an example of a free moving boundary problem, which usually are quite difficult to solve numerically. So to solve this problem numerically, and I guess you know where I'm heading to, we used the well-known diffuse interface model. That's Aurora was a leading expert on this model. We have seen several examples today where this model has been used. And in the case of imbibition, we basically have this diffusive equation that depends on the chemical potential, which is written in terms of this free energy. And now the free energy contains this stochastic term that models this quench disorder of the system. So the idea is that this model that depends on this other parameter that takes two limiting values representing gas and liquid, so the interface is defined where phi is equal to 0. You can take this, the width of this interface is controlled by this parameter epsilon, so when you take this parameter going to 0, you recover the macroscopic hydrodynamic equations, so that's the sharp interface limit. So this is something that we use for imbibition, and I have actually been using this model since I did my PhD. When I was a postdoc, we did some rigorous homogenization work on three-dimensional models of this this phase field model. So Aurora taught me this model, and I also convinced my postdoc supervisor to use this model for different problems, and also my PhD students are also using this model. So you can see that, Aurora, your influence has long-range effects and long-range correlations. So this is the model we use numerically, and let me show you an example of this. So that's for a spontaneous imbibition problem, which means that we impose the pressure here is constant. And as you can see, that's space, this is time. So the interface starts more or less flat, and then as the time goes by, roughens, and the fluctuations increase with time. So just let me introduce some basic concepts here to how to, we can. This is a numerical experiment. Yeah, so this is from the phase field model. So the idea to quantify this mathematically is that we're going to use scaling theory. So this is an example of a surface growth. And the idea is that there exists a correlation length that is horizontal and grows in time with an exponent z that we are now familiar after Rodolfo's talk. Is the dynamic exponent. There is also a second moment that grows within a power law behavior with an exponent beta. And of course, we are always dealing with finite size systems. So whenever this correlation length reaches the system size, then you get a saturated state where the second moment of the fluctuations scales with the length of the system with the roughness exponent alpha. And then you find a relationship between all these three exponents. So these three exponents are kind of giving you a global quantifications of the morphology of these fluctuations. And well, when I started doing my PhD, the state of play of this problem was the following. So there was the results that were done in Barcelona, where Aurora was very much involved on this, both on the experimental and the theoretical aspects. And these were experimental results done on a Hilly-Shaw cell involved in studying this imbibition problem. And the main result, one of the main results was the morphology of these interfaces were characterized by this set of exponents. So that was the draft that I was reading a lot when I started the PhD, and then it eventually got published in PRL. But there was a tiny problem here, is that a few years before that paper, there was another paper published by another group in Europe that were working on this problem, was the Helsinki group, led by Mikko Alava and Tapio Narisila. And they had done numerical experiments on the phase field model, although it was slightly different to the one that Aurora was using at the time. And they were reporting this set of scaling exponents, which, as you can see, are quite different from the experimental ones. So, well, there's some difference on the roughness exponent, but this is something that you could expect because the statistical properties of the material might be different. But this one, the Z exponent, is quite important because this one here, experimentally, a Z equal to 3 means that the dynamics of the system is controlled by surface tension. But this one here, it means that it's controlled by something else. So physically now is a key question that needs to be answered. So there was some more or less idea why this was happening, and Aurora basically asked me to take this model and try to reproduce with this model the experimental results. So that's what I did. I took this model, I numerically tried this in computation, and obviously the first thing I got was exactly the same results as they did. And I tried again and again and again, I was getting the same result, and I never observed the experimental results. And that was my first year PhD student, so I could either just go to Aurora and say, look, Aurora, this is not working, but that's not the best option to go forward, so I just kept harder and harder. And then I realized, well, we realized that there was a key important point here, which I should mention, and is that because this is a spontaneous imbibition front, so this means that this pressure here in the inlet is constant, and actually the pressure difference between the inlet and the interface is constant. So this means that the driving force is decaying in time, and then if you take the average of the interface, you see that this average quantity follows the well-known Washburn's law, which means that the velocity of the mean interface decays in time. So this is a crucial point because then when you look at the physics of this problem, you realize that there are two competing effects here, the surface tension and also the driving force. But because the driving force is decreasing in time, then you get an additional length scale that increases in time with a suspiciously exponent that is 1/4, which is very similar to this one, what is exactly this one here. So the reason why we have this difference in exponents is actually that there is a presence of this additional length which creates crossover effects. So if you want to observe numerically what is observed experimentally, we need to look at very, very low velocities where the driving force is very slow, and therefore the system is dominated by surface tension. And this is exactly what happened. So we did numerically experiment, well, which we tuned the model to reproduce very slowly driven systems so that the correlation length was always below this threshold additional length. So the exponent that we were observing was 3, as in experiments. We also then went back to experiments and tried to reproduce the numerics by increasing the velocity. So all this led to a series of papers, including one more theoretical paper in collaboration with Juan López, where we looked at the crossover effects in general surface growth. And this even led to a collaboration with the group in Helsinki, where Aurora basically sent me to Finland for 3 months. So you can see me here in the cold Finland. And so we published one paper together, and I think at the end everyone was happy. So that is about the morphology of the interfaces of this problem, but like I said at the beginning, also the dynamics of imbibition is very interesting. So I'm going to show you another numerical experiment where now we are forcing the system at constant speed. So we are imposing a very slow driving force at the inlet, and then we have this quench disorder present in the whole system. And what we observe is that the dynamics of these interfaces are characterized in terms of the pinning motion. So you can see that the interface at some points is like pinned, so it's not moving, and then suddenly it will jump to another location in a very rapid motion. So this is an example of intermittency and avalanche motion. So the reason why this happens is that we actually are close to a critical point here. The critical point is when the velocity is actually 0, and because we are driving the system with very slow forces, basically the system is a kind of intermittently jumping between the 0 state and the moving state. So there are different ways of quantifying this motion. I'm not going to go into much detail, but one of the ways that we looked is that if you take basically the average velocity over a window of length L, this defines a global quantity of this velocity, and you can see that this velocity is fluctuating in time, and is characterized by these large bursts of fluctuations followed by low periods of low velocity. So this is an example of intermittent signal, and when you look at the statistical properties of this, because we are close to a critical point, then we observe the standard second-order critical phenomena properties. So, for example, we see that the waiting times, which is like the time between 2 consecutive bursts of this signal is given by a well-defined power law with a nice exponent. Also, if you take the Fourier transform of this, you also get a power law in the spectral density. And so we have the exponents that characterize the morphology of the interface. We have the exponents that characterize the dynamics of the interface. So at the end of this, we ended up with a long list of exponents, and we managed to find a lot of different scaling relationships in collaboration with Juanma López. I must say that I probably forgot the half of the meaning of the half of these exponents, so don't ask me about this. And so at this point, we kind of were happy with the understanding of the morphology and the macroscopic properties of this problem. We had material which was around 7 papers, and Aurora didn't think that that was enough for a PhD. So then at that time she also was very interested in another hot topic at the time, which was microfluidics. So a natural connection from this is like, well, we have now the macroscopic properties well understood, so let's move into what happens into the microscopic scale of this imbibition process. So that's what we did. And then instead of looking now at the macroscopic average system, we are looking actually at the inside the microscopic pore, or let's say a microchannel. So now what we need to understand is how the liquid interacts with the solid. So we need to modify the diffuse interface model to take into account these interactions. And at the end of the day, what we are interested is to understand how the substrate properties may affect the dynamics of the interface. It's something that is a very important question, as we have seen, for example, in Rodrigo's talk, how can you manipulate fluids by changing the properties of the solids. So the model had to be modified to introduce these wetting properties, and that's then we include on the free energy this surface tension, this surface term, that when you minimize this free energy leads to this wetting boundary condition where you can basically control whether the system is hydrophilic or hydrophobic. And this leads to the following result. Now I'm realizing that that's the third time you see this slide, but I'm just going to give a little bit of more details about this. So what we look at is as a hydrophobic microchannel, which is decorated by this post, randomly placed, and then we impose a pressure here. So we observe that there are, I'm going to show you a movie of this. So that's an interface. And then we see that it gets pinned at the edge of the post until it touches the next and then continues moving. So there are two clear behaviors here. The first one is that the contact line has the pinning motion again. But also importantly, when the fluid keeps moving on that direction, and it leaves this interface suspended between two posts, which is something that is normally known as superhydrophobic state, which is a combination of topography with hydrophobicity. So we have seen already that this led to these rare events and extreme statistics. I'm not going to talk about this, but I'm going to mention that, at that time, no one was doing microfluidic experiments in the department. So Aurora thought that the best way to go forward is just to set up her own lab. So he created her own microfluidic lab, and so we did experiments. So there's a sketch of the experimental setup. And then what we did is to do numerical experiments and computations. And we observed, one of the conclusions was that because of the hydrophobic properties and a very small driving force, you can actually change the exponent of the washburn law. And we observed that this is experiment, this is computations. And as you decrease the pressure that you impose on the inlet, the exponent actually goes away from washburn and decreases to the value of 0.4. So this eventually led to this nice paper, which was published in Physical Review Letters. And now I think Aurora probably thought, you can write up your thesis, and now you can go away. So that's what happened. So now I wrote up the thesis, and finally I submitted and defended my thesis on the 30th of September 2009. And here a picture of the group at the time, which you have already seen. But I must say that when we were trying to look for pictures between Rodrigo, Felix, and I, we could only find two pictures. And you have already seen all of them, so I didn't have any other option to put the same picture here. But anyway, so that's the work I did. Okay. That's the work I did during my PhD. So then I moved to the UK, and I changed topic, but still with interfacial flows. And the problem I looked at is a thin film, particularly falling liquid films, which is something very common on rainy days. That's perhaps so you can see, for example, on a slopey road, when the film of water is falling down, you can see the emergence of these waves that are traveling more or less at constant speed. So that's an example of what is called a dissipative turbulence or interfacial turbulence, because these waves are coherent structures that are interacting with each other and creating nice wave regimes and nice wave patterns. So here the key parameter is the Reynolds number, which depends, well, there is a critical Reynolds number that depends on the inclination angle of this solid substrate. So if you have if the Reynolds number is above the critical value, then you have instability, and then the system evolves into this wavy regime. Otherwise, it's a flat film. And there are different models that you can develop depending whether you are very close or very far away from the critical Reynolds number. When you are very close to the critical Reynolds number, you can show that basically the equation describing the evolution of the fluctuations of the interface is the Kuramoto-Shibasinski equation, which we have already seen in the previous talk. And also, if you put some topography on the solid substrate and some sort of temporal dependency, which could be, for example, a very unrealistic case when you are vibrating the substrate, then this can be modeled with a noisy Kuramoto-Shibasinski equation. You can also prove this rigorously. So what we did for this particular case is that to study what are the effects of additive noise on this equation. So this has received a lot of attention. So what we try to do is to try to get some analytical and numerical analysis of this. And we look for a particular case and a particular regime, which shows a system which is very small or sufficiently small in such a way that there's only one global dominant mode that controls the dynamics of the system. And we put some sort of additive noise in the system. What we observe is that this noise is able to induce transitions. For example, for low noise intensities, we have that the solution is given by this fluctuating signal, but when you average these fluctuations in time, you get this pattern on space. But if you increase the noise intensity, then you get that the global dominant mode is completely stabilized and it goes to zero. So when you average the fluctuations in time, you get basically this zero state. And in between these two states, you have this intermediate state where the solution is intermittently fluctuating. So here is a critical point, and again, as it happened in the Bivision problem, we observe this intermittency, and again, when we look at the waiting times of this intermittency, we observe a power law with a well-defined exponent. So that's what happens close to criticality, an example of things that can happen close to criticality of this problem. But in more realistic physical settings, when we are small to moderate Reynolds number, what happens is that actually the system, this interface evolves into these solitary waves. And what we're very interested is to understand the interaction between these waves here. So the model in this case is much more complicated. It starts from a long wave expansion from the Navier-Stokes equations, and then you end up with this system of two equations for the height of the interface. And then the idea is that we want to study how these pulses or these solitary waves interact with each other. So let me show you numerical experiments. So I'm going to solve numerically this model for the thin film. And I'm starting from a random initial condition, but I'm solving the problem in the frame moving with the speed of one of these waves. Note that this is highly, the scale is not real, so this is like 1,000 and this is 1. So then what we observe is that from this wave, or from this initial disturbance, this evolves into a wave packet, and from this wave packet there are these solitary waves that evolve from it, and then they are interacting, and eventually they reach a kind of a steady state where they are separated by some distances. So the question is, can we predict analytically these distances, or they are just randomly placed? So in order to do this, what we did is to develop what is known as coherent structure theory. So basically we assume that the solution is given by this superposition of pulses or of solitary waves. And then this is rather technical, so I'm not going to go into details, but at the end you can find a dynamical system describing the location of these pulses. For the case when we have two pulses, then we reduce to this simple dynamical system for the separation length. And you can see that there are going to be fixed points where these pulses travel at the same speed, where some of them are stable and some of them are unstable. So this we can predict these distances, and now when we come back to this numerical experiment and we do statistics of this, so we compute basically the separation line between pulses and do the statistics of this and look at the histogram, we see that there are going to be these peaks, and this dashed line corresponds exactly to the theoretically predicted points where there are these fixed points in these two poles system. So this led to a series of papers where we studied different properties of this, and this is something that I started doing during my postdoc, and I continue doing now as a faculty member at the Open University. So just to summarize, just to use some examples of complex phenomena in interfacial flows. I would like to thank also the people I worked with at Imperial College, Seraphim, Greg, Demetrius, and Dimitri. And of course, the work I presented during my PhD was in collaboration with Juanma and Eugenia. And of course, I would like to thank Aurora for all the knowledge I learned from her, and congratulate you for this achievement and becoming the member of the Mexican Academy of Science. We have made most of the trip up in Mexico with Felix and Rodrigo. We went up to the top of the pyramid of Sol, of the sun, to charge our bodies with the power of the sun, although we got a little bit sunburn and a bit of rednecks. But with this, I'm going to finish and take any questions that you might have. Thank you very much.
Questions? Yeah.
About these coherent structures. Yes. Have you tried also with the, I don't know, like the Bene equation?
Yeah, with the Bene equation, the problem is that when you increase the Reynolds number, it blows up. So it's not physically relevant. So you can only study it up to a Reynolds number around 1, actually. And if you want to go beyond that point, you need to start using this type of more complicated models that allow you to go to Reynolds 20 and so on.
But Bene would, before blowing up, it does show similar...
Yeah, it shows this emergence of these solitary waves, but then at some point they just blow up. You need this system of 2 equations to be able to quantify this phenomenon.
I'd like to ask a question. For this paper problem, water invades this disordered media. Is the dynamic equation the same as KPZ? Or is
no,
not?
It's different.
It's different.
It's a good point, because in the 90s, everyone was thinking that these type of local models might be used to try to model this imbibition problem. But the thing is that these models are local, and you need to take into account fluid conservation. So you need non-local effects to model these systems. So the equation is not the same, and you actually it's quite different from it. Okay. It's a non-local equation.
Okay, so you have to have a conservation law of this, some extra, okay.
So all right. You have an integral.
You have some integral things, okay. Eugenia, yeah?
The distribution that you show with 3 peaks is the spacing between...
Yes, that's the space.
Are they harmonics?
Harmonics of
like multiples, can you put... I mean, I know it's a wavelength, right? Are they multiples of one another?
No, they are not multiples. Well, actually, they correspond to the minima of this potential, of this function here. So these are the fixed, stable points. Okay. So they correspond to the minimum of these distances, which depends on this wave, on the oscillations in front of the main hump.
Other questions, comments? Okay, if not, let's thank our speaker again. So the next speaker is Dr. Costas from this campus on highly viscoelastic forms at the water-air interface. Is he here? Oh, okay. Oh, okay, he's in the back. Oh, no, okay, it's him. Okay.
Perdón por el ruido. ¿Ya? ¿Se escucha? Bien. Y el control, entonces puedes poner esta. Ajá. Y tengo que venir aquí para echar a andar la película, ¿no? Esta avanza. Okay. Hello. Well, I want to start by congratulating Aurora for her becoming a member of the National Academy of Science in Mexico. So a lot of congratulations to you. And also, I want to thank Rafael and Eugenia for the invitation to give this talk. And I think I'm the only speaker today who has not done any collaboration with Aurora or published a paper with Aurora. Yeah, that's right. Mariano, you didn't. Okay, so I'm the second one. Okay. But I hope to convince her and Rafael and Eugenia and anybody else who wants to use the phase field model to understand and get deeper into the knowledge of the surface I'm going to talk about here. So I'm going to show you experimental results and give you some interpretation on that, but it's an interpretation which is not based in any model so far. I hope to do that in the future, and I hope that you help me to do that. By the way, I have to say that I met Aurora in a bar. Yes, in the physics, the winter meeting on the physics in 2002. We met in the bar with Eugenia, with Rafael, and we drank a lot of tequila. So I remember that one as a very nice gathering. Okay, so let me start.
That was memorable because
That was
converted into tequila.
Yes.
Right.
I think if I remember correctly, she said she had never tasted something like that, but she tasted that night. Yeah. Okay, so I want to start with a Chinese say that says that an image is worth 1,000 words. And let me show you what I will be talking about. Let me see if I can get this going. I hope so. Okay, I'll stop it here. Okay, so just to describe what you're going to see. What we have here is, oops. No, that's not what I want. Again. So we start again. Now. Ahí. Okay. I don't touch it. We'll touch here, no? Ah! Shit. Come on. Yes, that's right. I should do that. Okay. I don't stop it. So you can see here, that's the tip of a syringe. Okay. There is a tip of a syringe over there, and I'm injecting a liquid into air. This white part is air. And you can see what happened. I'm going to run it again. It's only 13 seconds. I want you to pay attention to the neck that is formed here. So look at the curvature here. So the drop sort of distorts and has a narrow neck. And if you wait a little bit, you will see that, well, you have seen it already. You will see that that curvature changes drastically to get into a drop which is then stable.
And the white part is just light reflection, or it's a?
It's air, yes, and light reflection, yes. Okay. Which is the? No, the pointer. Okay, fine. Okay, so the point here is which are the actors of this movie? So, in other words, what was in the liquid? So the liquid here has three components. One component is called alpha-cyclodextrin, and this is a very interesting and funny molecule. It's produced by millions of tons every year, and it's used in many, many, many applications, from medicine to cosmetics to anything else, to pharmacology. And it's a molecule that has it's a cycle, and it has a shape of a cone, like a sort of a truncated cone, in which the hydroxyl groups, I'm talking as a chemist here, make the molecule being soluble in water, but the interior part of this cone is hydrophobic. So this is illustrated here. This is a cyclodextrin. This is a hydrophobic molecule, can be anything, a hydrophobic part of a molecule. And this can be solubilized inside the cyclodextrin, forming what is called an inclusion complex. So these molecules are used, for example, to encapsulate drugs or to encapsulate active components of many other kinds. The second component is a simple surfactant. In this case, in this presentation, it's an ionic surfactant, which has this formula. It's a chain length, a hydrophobic chain length with a polar head. And we used the chain length of variable size, 8, 10, up to 14. And we also use one in which it is 12 carbons long, as this one here, but we change the head by substituting one oxygen, and that makes, well, a difference. And the third component is water. That is the liquid you saw in the movie. Okay? Now, we studied the binary solutions, which are quite boring. Nothing spectacular or important happened there. That is the alpha-cyclodextrin plus water and any surfactant plus water. The interesting thing comes when you have the three of them mixed, and that's what the movie was about. So, what is it that we measure? Well, we try to measure I think it's obvious, or it was obvious for us from the movie, that the interface between the liquid and the air in that movie, there must be some film or some structure that is elastic, because otherwise it would be impossible for these changes in curvature, for example, the distortion you see in the drop, at the beginning of the movie. So we decided to measure the dilatational rheology of the absorbed material, let's call it that way at the moment, at the air-water interface. For that we design a system. I want you to pay attention here. This is the drop, you see it there? That's the drop, and it is in an environment at constant temperature. And we have a camera which has 123 frames per second, and we designed this cell to be able to do the measurements. Now, this is called the pendant drop technique. One can use a sinusoidal periodic oscillation, where we can change the frequency, and we go from 0.01 to 0.2 hertz. You can choose which one you want. We use 5 or 6 of them. We solve the Young-Laplace equation to obtain the interfacial tension, and we also get the interfacial area. So these two values are the result of the experiment. By using many frames, we solve this, the Young-Laplace, and we can get the dilatational modulus, which is the change in the surface tension respect to the log of the area of the drop. Also, we have a phase change between the area and the interfacial sinusoidal oscillations. There is a phase change there. And then that allows us to get the elastic and viscous components of the total dilatational modulus. And when this is 0, it's purely elastic. When it's 90, it's purely viscous. So the measurements, the initial measurements, were done at 2 temperatures, 10 and 20, for the 5 surfactants I show you, at 5 frequencies, and we use many different concentrations. We define it as R is the concentration of the surfactant divided by the concentration of the alpha-cyclodextrin. So let me go right away to the results. these are the results. This is the dilatational modulus. This is the concentration, or the ratio of concentration. This is at 10 degrees, 0.2 hertz, the case of Tom. And there is a 1.5 equilibration time. What does that mean? When we form the drop, we can be monitoring the surface tension. And the surface tension changes with time, and at about between 1 hour and an hour and a half, the surface tension stops changing. It becomes stable. It's an equilibrium state. So we have all of this data were obtained once whatever is in the surface has reached some equilibrium. So here you can see what happens with this E. This is for C14, the longest chain. The blue is C12, C10, and C8. Let me move this. I want you to notice that for when the chain length of the surfactant is 8, there is no elasticity at all. When you increase the chain length, then you get a larger elasticity. Also, for the binaries, that is surfactant water and cyclodextrin water, it's 0 also here. So the binaries are not funny.
Sir, these are millinewtons per meter.
Yeah.
So that means that it's huge.
Yeah, that's what I was going. In the literature, the biggest value we were able to find for dilatational modulus is 90. And you can see 90 is run down here, no? So this is about 3 times, no? It's a huge effect. Actually, it hasn't been reported values above 50 for any system of any kind. So it's, that's why the title of the talk is highly viscoelastic, because it's really highly viscoelastic. Yeah, it's big, it's big. And then, then they notice, I will come back to this goes increasing, E increases, and then drops, and then the blue, all of them finish dropping. This value here is very close to the value of the binaries. Okay, that will become relevant a little bit further away. Now I use an English say. There is an English say that says that what's bred in the bone will come out in the flesh. And if I translate it to the case here, is I could say what's bred in the bone, the bulk solution, will come out in the flesh. That's the surface. So the question here was, what is in the bulk solution? Because whatever is in the surface comes from the bulk. And in surface science, we know that, well, perhaps you not so much, because many of you work with pure fluids, pure water, for example. But if you have a mixture, what you have in the surface is a consequence of a part of what you have in the bulk and the organization you have in the bulk. So we ask that question, what do we have in the bulk? For that, we use isothermal titration calorimetry, which very quickly is you have in a cell with temperature control and so on, you have one of the components and you titrate the other. And when this interaction gives place, it produces an absorption or desorption of heat, of energy, we can detect that. So how much we can detect? Well, the detection level of this calorimeter is about 0.1 microwatt, sorry, and that is equivalent to this is the quantity that you would detect in a 1 meter square panel 10 kilometers away from a bulb of 100 watts. This is the amount of energy we are able to detect in there. So what happened? Well, these are the curves. This is for the case of C12 from 10 to 50. It doesn't matter. This is the heat. This is the concentration. And the point is that here, if you assume that in the bulk this is happening, that is, the surfactant gets inside the cyclodextrin, forming what is called a 1-to-1 complex. And this one can take another cyclodextrin and form a 2-to-1 complex. If you do that assumption, you can fit the data almost perfectly. So what do we have in the bulk? We have free surfactant, free alpha cyclodextrin, and these two types of complexes. Now, what you get from the experiment is the equilibrium constant of this equilibria, K11 and K21, and the enthalpy change for the formation of these complexes. And from this data, it's quite easy to calculate what we call the distribution of species at equilibria at that particular temperature. So this is, for example, the distribution of species at 10 degrees for C12. So this is the concentration, and this is the concentration of each one of these 4 guys who are in the bulk. So for example, the black one is the free cyclodextrin, the red one is the free surfactant, the 1-to-1 is the blue one, and the 2-to-1 is this one over here, the orange one. What's remarkable about this is that the 2-to-1s are really dominant. And there are concentration regions where actually all what you have in the bulk is 2-to-1s. And as you increase the concentration, of course, the other ones start to appear. So we have the contention that what's in the bulk is 2-to-1s essentially, and that is what causes this. In other words, let me put it, that at the water interface is populated by the 2-to-1 complexes. And so, for example, these are the distribution of C12 and C14, and this corresponds more or less, roughly, almost to the maxima on E. Now, why it drops? Well, it does happen that the point it drops is when the 1-to-1 and the free surfactant are enough in the bulk to go to the surface. And the affinity for the surface of the free surfactant is bigger, larger, than the affinity for the surface that has the complexes. So in other words, I think I wrote it here, the 2-to-1 complexes organizing the surface, probably through some electrostatic interactions, producing an elastic film. And as the concentration increases, the elasticity increases until the 1-to-1 complexes and the free surfactants are available in the bulk. They go to the surface, perturbing this organization and kills the elasticity. Actually, the values here at large amounts of surfactants are equal to the value for the binary surfactant water. So the surface changes composition, and while the composition is 2-to-1, you have a large, very large elasticity, larger for the longer chain, and then it drops because this 1-to-1 and the free surfactant go to the surface, displace the other ones, and dominate the surface. And they are much less elastic. So this is, we did a lot more experiments. We asked what's the effect of temperature. So we did the same experiments. This is the case of C12. And we want to know the effect of temperature and the total amount of material. That is keeping the same ratio R, but increasing the amounts of each one of them. So the result is that, well, first of all, the temperature, it is more elastic at 10 than at 20. And actually, at 25, at room temperature, this value goes practically to 0. So it's extremely temperature dependent, and the cooler it is, the more elastic it is. Then the amount of material, this is the amount of alpha cyclodextrin in the mixture, but all of this is at the same ratio of concentrations, and it increases and then levels off. So if I put 10 and a certain amount of surfactant to get a given R, and now I put 12, so I double them, the elasticity well goes from there to there, for 120 to 150. So it doubles the elasticity. Probably because the surface is better or more populated with the 2-1s because there are more 2-1s. But it gets to a point in which there are no room for more 2-1s, and then it levels off. Then we also ask ourselves, what's happening if I mix surfactants? So in this plot, what I show is that I start with the C12 only, and then I add C14 or C8. So, for example, if I add C14 at these ratios, the elasticity becomes even bigger. And if I add C8, it becomes, it's lower. Remember that C8 alone has no elasticity. So I can kill the elasticity by adding C8 or make it even bigger if I add a little bit of the other one, of the C14. And finally, we also did this experiment in which here I'm plotting the surface tension against time. This is after the 1.5 hours to reach equilibrium. For example, the red one is at 20 degrees. And then we repeat the experiment, that's the yellow one here, and here we suddenly change the temperature from 20 to 10. So the surface tension comes down here, and then at this point we change back to 20, and the surface tension goes up again. If we do it from 10, it's the same. The blue one is 10. The, what's this color? Purple. It starts at 10. At this point, we increase the temperature from 10 to 20, and the surface tension goes up. Here, we decrease the temperature again, and it goes down again. So from here, we say that the film in the surface is reversible in the sense that we can come and go with temperature. Also, there is no hysteresis, clearly, in this system. So in general, what we can say is that the film viscoelasticity can be set up to a given desired value or range of V values. So if one of you tell me, I want an interface liquid air of 125 millinewtons per meter, I can do it by several ways. I can use a certain surfactant at a certain temperature, or I can mix that surfactant, or I can do several things. So this is important for possible future applications of this kind of surface, because it means I can control the surface. I can control how much elastic it is or less elastic it is, at will. Or, well, almost at will. And of course, I have a small range of temperatures and so on, but nevertheless, there is a certain control. Then we ask, what's the thickness and composition of the film? So for that, we apply for Newton time at the facility in Grenoble, in the Institut La Jouvin in Grenoble, to use the facility for neutrons, for surface. They have a special apparatus for that. And we did it at 10, and we did it with C12. We use what it's called for contrast, that is the C12 protonated, fully protonated, plus alpha CD in D2O, the same one plus alpha CD, but NRW. NRW means non-reflecting water. Non-reflecting water is 8% and more of D2O and 92% of H2O. And it has a very nice feature that it's insensitive to the neutrons. So when you put a system in NRW, you're really looking at only the surface, not the substrate, which is essentially water. No? And then you use the deuterated surfactant in the same two media. These are the four constants. Why we did it only with the C12? Well, two reasons. First, because in Grenoble they give you 48 hours, and that's it. And you have to work non-stop, because otherwise you don't get data. And the second is because it's very difficult to get the other surfactants fully deuterated. So we did it for 12. Now, the points are here in these plots. Here is essentially the reflected divided by the incident neutrons. Here is the wave value, Q. And these are for different concentrations. The points are the experimental values in these four contrasts. Using what is called the Parrot method, we were able to fit simultaneously the four. So what you see here in these lines, blue, yellow, and so on, are the simultaneous fit of all of these curves to the experimental data. what you get from here is, well, first of all, the model that worked was a one-layer model. The thickness is only 2 nanometers. We were expecting, yes, thank you. We were expecting a thicker layer, but it wasn't. It was 2 nanometers. Now, 2 nanometers is about the size of one of these complexes 2-to-1, where you have here the surfactant, and then you have the 2 molecules of cyclodextrin. So it's essentially a monolayer of 2 ones, okay? And now the composition at the air-water interface, it's given here from the fitting. We can calculate that. And for example, here is the free S. Please notice that here it's very, very big. For example, at this very big R, the elasticity is 0 because it has so much surfactant that it's taking the surface over, and the elasticity is killed. Here is where it's maximum. The 2-to-1s are again the more important ones at the surface. The 1-to-1 are the blues, and the water is the red ones. So the surface is composed by some organizations of the surface that produces a high viscoelasticity is composed by 2-to-1 complexes, water, and that's about it. And of course, I can move to the left of that or to the right of that and change the composition of the surface. Now, we don't know how is the organization of these complexes in the surface, but we have some hints, and the hint comes from actually many years ago, which is the organization of the 2-1 complexes at the surface. Well, the answer to that question is we don't know. And we hope to learn that, for example, applying or have a better idea, applying a model to this data to understand what is that organization. But if the film is deposited on mica and dried, I put dried in quotation marks because it was not perfectly dried, but just dried. And we did this with Rolando. He's sitting here many years ago, what, 10 years ago, maybe. Using AFM, atomic force microscopy, we get this. You can see here, oh, I forgot to put the scale, but believe me, this is long. This is quite long. And you can see there, like the tubes organized, and that's why we call it nanotubes of 2-1 complexes are the building blocks of that. So the organization of that surface, once you deposited it in a substrate like mica and get rid of part of the water, is this, nanotubes like this. We did some molecular dynamic simulations, and this is the top view, and this here is like this. Okay, you can see the 2-1, and follows another 2-1, another 2-1, and so on and so on. And these, in the simulations, remain stable. They don't sink, they don't break. Well, finally, these are the collaborators of this work here at UNAM, in Mexico, in Coajimalpa, in Spain, and also in the Czech Republic. This is the money comes from there. And well, thanks for your attention.
Thank you. We have 1 minute for some question. Yeah.
Yeah. Miguel, when you introduced this Feldman-Roth technique, you said that you somehow have some periodic oscillation.
Sinusoidal periodic oscillation.
Some frequency range. That is imposed on the drop, right?
Yeah.
So, but I wonder, like, if you have a way of measuring, like, the viscosity also, because you have been talking about elasticity.
No.
But since viscosity might change with this frequency, I don't know how much of the effect that you are seeing can be attributed to viscosity and how much to elasticity.
Okay. I cannot measure viscosity, but I can show you the two distributions, the two contributions. These are E prime and E. So the red one is the viscous contribution. The blue one is the elastic contribution. These are as a function of frequency. This is the biggest frequency I can use in the instrument. And these are different concentrations. For example, the maxima for C12 is here. There is a small crossover here. But essentially, well, this is more or less the answer to your question, no? Is the viscosity part and the elastic part. They are quite similar, or more or less the same magnitude.
Okay, because all the results that you show, like did you show them at the fixed frequency or
Yes.
you're mixing?
No, all the results I show are at a given frequency, 0.2, but we have the same results, but at every single frequency we used. I just choose to use 0.2.
Typical behavior.
Yeah, that's right. If I show you the data for 0.05 frequency or 0.01, which is the smallest one we use, they will look the same. Slightly less, slightly, but basically the same.
Since our next speaker went out, so we can have one more question.
Okay.
It was more or less the same question about
Okay.
the viscoelastic spectrum.
Yeah. So you see, Rolando, you that are an expert on this, in the literature we only found this kind of crossover between viscous and elastic for shear rheology. But for the natational rheology, we were unable to find any report on that. Now, it's not a spectacular crossover, but we're pretty sure of this data, and the errors here are pretty small. So I think it's clear that, for example, at low frequencies, the viscous one is dominating over the elastic one, and the contrary happens at the other one.
I guess
at the maximum.
The most important thing is out of the same order.
Okay, so our speaker came back. So let's leave your question at the dinner time, okay? Because it's getting late. Okay, you ask a question. You set up.
Your dilation modulus to the Young modulus, like in the Nisi way?
Yes, you can. I don't have here the...
Vaguely, how would you do that?
Oof, well, I think that, to be honest with you, we look at that, but for some reason we said, nah, we don't need that. So we didn't finish doing it. I am pretty sure you can do it, but I haven't done it, so that to show you the results. But I would say that you can do it. I think so.
Since he's setting his presentation, I have one more question.
Okay.
So what's in principle, the physics behind changing surface tension with small changes in area? Like, what's the physics behind? Like, if you have a normal surface, you change area and your surface tension doesn't change, right?
Mm-hmm.
So, but here, this dilation index is basically the rate of change of surface tension.
Because we're getting very...
Not with area, but with the logarithm.
With volumes, yeah.
So, like, is there a...
Well, I'm not sure I understand your question. The principle of the experiment is once the drop is at equilibrium and quiet, let's put it down, then you oscillate it at a given frequency. In every oscillation, you are increasing the volume and decreasing, increasing and decreasing, and you are all the time taking pictures of that and solving the John Laplace equation. So you follow how does the surface tension of the drop of the same, the same drop all the time, changes with the increase and decrease of the volume or area. And well, if you look...
it's just that the John Laplace equation is an equilibrium equation, right?
Yeah.
And then you are like using it as adiabatically, you are in quasi-equilibrium while your drop is moving, right?
Yes. And we assume the temperature is constant.
Okay, let's stop.
So we
let's stop here,
that we are...
because they are waiting for you.
Yes.
Yeah.
That way we waited 1.5 hours to be sure that the drop is not moving or changing before applying the oscillation. The movie I show, it is at the very beginning, so that's out of equilibrium. But it shows nicely how the surface distorts and changes. I mean, to me, that change of curvature from this one to the other one in the neck is spectacular. When you look at that, you say, what do we have there?
Okay, let's thank our speaker. All right. Yeah. Very interesting discussion, but let's leave this to the dinner or something. Yeah. Okay, our next speaker, I forgot to say, is Professor James Glazier, and he will tell us magnetization to morphogenesis.
So, I met Aurora for the first time in 1986 at Les Ouches, and I've still never published with her. And you've heard a lot about phase field solver methods. You're going to be hearing about a different approach today, and that's really going to be the only mathematics or physics in the talk. I'm going to be reviewing a lot of work because I had to go back to basically 1986 to have anything with statistical mechanics in it. So that's why there's a long list of people who've worked on these problems for the years. My interest is in what might be called biophysics or bioengineering, really pattern formation problems in living organisms. In particular, how you build an organism. Something that physicists don't think about usually so much, which is how you maintain an organism, because we're not static equilibria, we're actually dynamic, and actually maintaining a structure over long times, as we saw in for example, the growth phenomena when you're wetting paper, actually maintaining a structure is difficult if you have continual dynamics. That's called homeostasis in biology. How homeostasis fails in what are called developmental diseases, of which the most famous is cancer, but there are many. And then ultimately how you can do bioengineering to design tissues or other systems. All of these are self-organizing pattern formation problems. In a sense, I've stayed truer to traditions of pattern formation than many of the people I was involved with, like Joel Stavans. And so the only reason that I've got the word magnetization here is that we started, back when we were graduate students, doing experiments on soap bubbles with Joel. And then we worked with a group at Exxon doing modeling of soap bubbles, which was based on extensions of the Ising model. And the question is, how on earth does that have anything to do with the elaborate developmental phenomena that you see in these biological systems? And the answer to that is that these are all soft cellular materials. They all involve domain interactions of various kinds. They all involve stochastic fluctuations, and they all lead to temporally evolving domain or organized patterns. And the key question then, if you're going to try to build a biophysical representation of a tissue, is how you describe the configuration of the objects in the system, what the forces, or as we've seen in talk after talk, very often it's easier to use potential energy, what I would call an effective energy formalism, rather than an explicit force formalism. So the forces are the gradient of the effective energy. And then you would need some kind of dynamics, which translates how things actually move in response to forces. And so as far as the very simple statistical mechanics goes, we go back to the Ising model. We write down a magnetization. In the Ising model, you have typically two spin states. And you have, if you're solving it numerically, typically you use Metropolis-Boltzmann dynamics. where you pick a site at random, you update that site to be the opposite value. You accept the update with some probability that's Boltzmann weighted by the energy penalty and the temperature. And then, of course, that gives you a pattern. In the 1940s, and late 40s and early 50s, Potts extended that to say, what if you had multiple equivalent states, degenerate spin states? The answer is you don't get something that's very different, except that when you do your update, you're picking from a list of possible states rather than just a single state. If you want to look at foams, it winds up that many of the properties of the Potts model apply to foams or to metallic corseting. However, there are some differences. In particular, you have now a boundary dynamics problem. And so you don't have detailed balance anymore. Once something disappears, it doesn't come back. Boundaries only move at the boundary. You don't have heterogeneous nucleation in the center. And what you're really interested in now is the dynamics rather than the equilibria. And so the simple way to achieve that is that instead of having your lattice updates be global, they're local, where a lattice value can overwrite a neighboring lattice site. And that modified metropolis dynamics then gives you what you want. And so those are the changes that one needs to build a simulation of this kind. If you analyze that and you have some kind of effective energy H, it's a function of configuration, then you have an effective force on the system. That's the gradient in configuration space in some high-dimensional configuration space of the effective energy. And if you're careful so that your gradients aren't too big, the velocity is linear in the force. And so you have overdamped movement of objects. And so you could use this now numerically to solve any Hamiltonian system, and the evolution of that quasi-Hamiltonian system then will be linear in the force. And it doesn't matter what it is, what the H is, it can be anything. And so this is a numerical methodology for solving evolution equations of particular systems. And if you do that in a simple way, you get this kind of corseting behavior, which is typical of foams. And this goes back to the work we did with Joel and then with the team at Exxon Research. In those days, Gary Grest, Michael Anderson, Srolovitz, and you can see the dates here, 1980s, 1990s. And it works, one thing that's nice about this compared to some other methodologies is it works equally well in 2D and 3D. There are no changes going from 2D to 3D. If you look at simple embryonic tissues, there's a classic experiment where you mix two cell types from an embryo and they phase separate. This is called cell sorting. It was work done by the late Malcolm Steinberg going back to the 50s. And that kind of phase separation is something that looks familiar from all of these statistical mechanics systems, except, and we've heard this in other contexts now, the temperature in the Boltzmann factor is now replaced by a fluctuation amplitude which is much larger, which is driven by the cytoskeletal fluctuations of the cells. It's not the temperature in the room anymore. Now, we don't see corseting in cells. The cells have defined volumes, typically. They have other properties. The adhesion energies between cells can be very complex. And so you need to extend this simple model by allowing energies between different interfaces to vary. And by putting volume constraint in. And we've seen these terms, all of these terms have shown up in talks earlier today in other contexts. And so now we can do things like write a differential equation for a target volume and have our cells grow. And in this case, we have an algorithm for cell division. I said we didn't have net nucleation. That has to be put in from outside. This is a simple cancer simulation. We could also do the cell sorting simulation. Here we have two cell types. All the cells have the same volume. There's an interfacial energy where green cells have a slightly less cohesive or slightly less cohesive than blue cells. And so there's a gradual rearrangement due to fluctuations that leads to full phase separation. And so that's a classic experiment. Goes back, as I say, a long time in experiment. This is simulations also go back quite a while. I think they published that in 1993. If you want to really model tissues, there are a lot of things going on besides cell growth and cell adhesion. And so now you have to think about how to extend this kind of formalism to include the other things that cells do. Simple things like membrane area, potential viscous interactions, because this system is actually fundamentally a fluid system of a particularly strange kind. Elasticity, because there's no concept of solid in this system. And other things like cell death, cell division, and also interactions with the outside world. In particular, we've heard a lot about fields of various kinds and interactions with fields. And so you have a concept of diffusing fields, which could be chemical, electrical, and other. Those can be absorbed by cells, secreted by cells, and so on. And of course, unlike typical physical objects, biological cells have complex regulatory apparatus sitting inside of them, and so you need to be able to model that as well. And so what tend these days to be called virtual tissue simulations essentially break the analysis of tissues down to three components. You have some model of signaling, regulatory, metabolic networks inside of each cell. You have some model of what the cells themselves are doing, which is based on this statistical approach. And typically, there's a big problem, which is that we actually don't know how chemical concentrations translate into cell behaviors very well, which is why most of the bioinformatics, genomics, proteomics that gets done doesn't really actually tell us very much about how organisms work, because we can't connect those molecular concentrations to the behaviors we care about very easily. And then we need to couple the cell behaviors to the environment. Here is an example of a simulation of the segmentation in the chick embryo, which is going to lead to the rim pattern in the organism. This has a subcellular model of oscillating chemical reactions, diffusion model of morphogens, and then the cell behaviors actually changing in response to those. So these models are pretty complicated, and so we've spent a lot of our time doing something which physicists tend not to do so much, which is building software tools that allow people to build these kinds of models. And so for the past 10 or 15 years now, we've spent time building a software structure. Ours is called CompuCell. These days, there are quite a few of these available. When we started, this was the only one. That allow you to define these relatively complex models in terms of more or less biological concepts. And in our case, they're scripted using a simple Python script. And so you could write a simulation of the kind I showed there in 100 lines of Python sitting on top of 500,000 lines of C++. And so that means that people like biologists or clinicians or students who don't want to have to write 500,000 lines of C++ can actually do this. And so that's been really a big part of what we do. The methodologies we're talking about are lattice-based, and they have their pathologies, and so we're actually working on developing tools to do more classic solids-like modeling, where we actually have explicit triangulations, tetrahedralizations, and that does better for the mechanics off lattice. Probably be another year or two before we have the scriptable version of that available. And so let me give you just quickly, because people are tired, some of the examples of things we've worked on over the years. And again, our goal is as much to get other people to build models of this kind as it is to use them ourselves. So these are just demonstrations of some of the kinds of things you might be able to do. You might ask, for example, why when you take acetaminophen, which is called paracetamol in Europe, a certain fraction of people who take that will die of liver failure. especially if they've had a drink and they take it in the morning after drinking the night before. Why you have neoangiogenesis, which can cause blindness in the retina. Why some people's kidneys never stop growing and keep growing till they die. Or why cancer treatment could cause cancer to become more aggressive rather than actually curing it. And so here was a simple simulation of cancer, what's called somatic evolution cancer, done primarily by Gilberto Thomas, who's a frequent collaborator of ours from Brazil, from UFERGS in Rio Grande do Sul, studying the evolution of behaviors in tumor cells. This is a little simulation of vascular tumor. It's an old simulation, but it's pretty, so I like to show it. This is actually comparing the growth of tumors when the tumor has to take its nutrients from pre-existing vasculature to the case where the tumor is able to induce new vasculature growth in the tumor. What I want to say about all these simulations, and I'm skipping over, you could give a whole talk on each one of them, is simply to show all of these simulations were written in the same environment. None of them have more than 120 lines to specify them. This is more recent work on kidney, this kidney disease that I've talked about. This is a lethal genetic disease. Cancer is often talked about as a genetic disease. It's not. Cancer is a disease of cell behaviors. This one happens to actually be a genetic disease. If you have a mutation in the polycystin 1 gene, you will get the disease. If you don't have that mutation, you won't get the disease. However, the mutation is in a gene that seems to have nothing to do with what the disease looks like. And so the question was, could we in fact analyze what's going on? And since we like cell adhesion, we modeled it as a cell adhesion defect. And in fact, it winds up, it is a cell adhesion defect. And we're now trying to get into clinical trials on some treatments for it. This was a simulation where we actually did some explicit fluid calculations, not as pretty as the ones we've done here, but you can do it in this methodology if you push it, where we're looking at transport of a drug, in this case acetaminophen, into the liver, its metabolism, and then the level, what happens to the level of the drug in the bloodstream. And again, you could understand then why some people are susceptible to killing the liver from that disease. The thing I'd like to talk about just a little bit, and I know we don't have very much time, is a project that I would love to see continue, maybe be some interest here, which is diabetic retinopathy. So all of us as we age lose some of the blood vessels that supply oxygen and nutrient to our retina. And this leads to some gradual visual degradation in all of us. It's normal. However, if you're diabetic, you have radical and deleterious restructuring of the vasculature in the retina. In particular, you see that you get tortuous vessels, which are typical of high levels of growth factors. You have loss of vessels, you have edema, leakage because of chronic inflammation in the retina. And at the moment, we can't really predict what's going to happen, either at an individual level or more specifically locally in a retina. And this is an issue because some diabetics who seem to have their diabetes very well controlled will go blind from this. And some diabetics who seem to have their diabetes very poorly controlled never have a problem. And so clinically there's an issue. And this was worked on in collaboration with some ophthalmological surgeons and Xiao Fu, who's now at the Crick, former student. And the work has been on hold for 2 years because when you have a really good student like Xiao and he finishes and does something else, then it's hard to replace him. So if anybody wants to come and replace Xiao, you'd be most welcome. The current way of treating this disease is highly medieval and sort of Spanish Inquisition style. You go in with a laser and you kill the photoreceptors in patches to try to reduce the oxygen load on the retina. So the hope that you reduce the level of demand for oxygen to an extent where the vasculature can support it. This is not a crazy idea. When you fight forest fires, you cut fire breaks, and this is basically a contagion model of this kind. The problem is that when you fight forest fires, you actually calculate where you could block the fire. You don't just randomly cut down patches of forest and hope that you've found the places that are going to block it. At the moment, that's how it's done. They just randomly come in. Of course, when there's one of those white spots, there are no photoreceptors, you can't see there. And so this is a case where the cure could be as bad or worse than the disease. And if you look at the clinical literature, you have this wonderful note that this patient had to go through this treatment 8 times, and it still didn't work. So not only does it cause damage itself, it's actually not very effective always. Some people it's fine. They have one treatment, they're fine, but a lot of people don't. And so the question was, could we actually build a simulation which would predict how this contagion would happen, and therefore you could calculate where you should ablate, minimize the area of ablation, so on. And so we did some fluid models. We could certainly use better models of blood flow and capillaries for this. These are very simple Kirchhoff type models based on patient retinal scans. You can then calculate the oxygen tension roughly in the retina, calculate what the production of growth factors, in this case vascular endothelial growth factors, the typical output of the cells that don't have enough oxygen. If that gets to be too high, the blood vessels react in a bad way and you have the pathologies. And so then you could build what's called a risk map, which is to say that if randomly such and such a vessel breaks out, this is likely to cause the vessels near it to fail or not. So if they're red, that means that if those guys fail, they're likely to cause contagion. The blue ones, if that fails, doesn't seem to make a big difference. And so now you could say that if I'm going to build a fire break, I should build it next to the red ones and not to the blue ones. And so then you could actually do some little simulations where you try to see what the efficacy of different treatment patterns would be. And then you could ask the question, if you don't treat at all, you have loss of vision due to the progression of the disease. If you treated and ablated the whole retina, you wouldn't have any progression of the disease, but you'd be blind. So you could then ask the question, what pattern and amount of treatment give you the optimal balance between the damage from the disease and the damage caused by the treatment? And so that is an example, again, in a very simplified version. What we want to do now is, what we would really like to do now is go back, get whole eye data from patients in series, and continue this to actually turn it into a treatment. Because it winds up that these treatment devices are programmed, the laser is programmed to ablate, so if you could actually calculate where to ablate, you change the software, you don't actually change the hardware to make it work. And so I'd love to find some people to work with on this problem. There are actually a lot of subtleties about how you do the image analysis, how you calculate the flow, how you optimize the model of the feedback here. But those are individually soluble. We have a sort of proof of concept for this.
These are different patients or are the same patients and
No.
they evolve in time?
So this is a toy, this is just a demonstration. So each one of these is the same array of blood vessels. And so what we are checking here is if we ablate in different patterns, what is the propagation of damage from the disease? And so here what we are saying is that, now, these are all stochastic models. The propagation of the disease itself is stochastic. So you run many replicas, which is why you have notch, box, and whisker plots here. But these are for just one example.
Then you would say it's like the same group of patients, like evolving in the disease.
No, so this is simply, these are simply statistics for treatments. This is for one virtual patient asking the question, again, I could easily talk an hour on this one topic, and so I'm just going to go over a lot. This is saying here, this first column is if we don't treat at all, how much damage is there going to be at the end of the simulation? If we treat a lot, how much damage is there going to be? This one is the damage from the disease, okay. This one, then the other one is the damage from the treatment, and so you have some net, which is the sum of the damage from the treatment and the disease. And so you get, it's not perhaps very convincing, but you get this vaguely U-shaped curve, and that one is the one you would pick, ideally. Again, this is a proof of concept. In a real patient, you'd have a much bigger area to look at, and you would run more replicas and more treatment patterns.
And is it possible to really do laser to that level of precision?
Yes.
To focus wherever you want?
Yes, that's right. That's not a problem. One of the things that's interesting about the eye from the point of view of modeling and design is that in general it's very hard to do experiments on humans and it's easy to do them in animals, except in the eye. Ophthalmology has developed amazing technologies to look into eyes and to do things to eyes, but they are all completely tied to the geometry and refractory properties of the human eye. So you can't do any of this experimentally in a mouse because the eyes are too small, they have the wrong shape, and their refractory properties are different. You can more or less fit a human one to a pig eye, but in general, it's easier to do it in a human. And in general, these experiments to do the observations are not invasive. So you have to get permission and so on, and we're not at the stage Aurora is where we have patient data. We're negotiating that at the moment. But in principle, at least doing the prospective calculation of to see that your model is valid is something you can do in humans quite easily. You take a patient who's not being treated, yes, that's right. You take a patient who's not being treated, but who has diabetes, they come in every so often, 6 months, they have a new scan. What we need is access to that data so we can check that we're actually predicting the damage profile. So those are a couple of things that you could do. As I say, it's a very short version of this. But gives you a flavor for the kinds of things you could ask. Well, as I said, all built on this same platform of modeling. Now, as these models become more complex, this Ising-Potts substructure of the model gets more and more hidden. It's really just used as a mathematical relaxation technique, like a immersed boundary method or any other. It has its own advantages and disadvantages, its own pathologies, and so on. But it is simple, and it's pretty fast. And I certainly never thought when we started working in this methodology 30 years ago that the methodology itself would be so flexible that we would still be using it to do things that it was never intended to be used for. In other words, basically you don't really think that you're going to be studying retinal damage with the Ising model. And so to me, that was sort of the moral of this. Perhaps that some of the same things apply to the phase field models, although the phase field models still are staying closer to fluids, perhaps, than this. Most of these biological and medical problems that I've shown you are problems that came to us. In other words, somebody knocked on the door and said, we want to collaborate on this problem. And so we're always looking for people who want to collaborate. There are a lot of interesting problems still to be done. This software is open source. It runs on Macs, Windows, Linux. And we teach every year a course in how to build these models. We've had people from UNAM come and take the course in the past. Our next one is August 11th through 17th in Indiana. So if anybody wants to come and take the course, that would be great. If somebody wanted me to come down and teach the course here, that would be fine too. It would be fun. I discovered that the people here at UNAM who use our methods now actually took the course when we taught it in Brazil at Porto Alegre a number of years ago. We got international grant to teach the course and a lot of other methods too. It calls a PASI, Pan American Science Institute, in Porto Alegre, co-organized with Gilberto Tomas. Funding, well, in principle, when you go back, you're supposed to list all the funding that applied to the things that were funded. That's why it's a long list. The current grants are the ones that are highlighted there. And so please, if you want to work with this, it's great. If you want to try it out, if you need help, if you want to try it, that would be great. I want to tell one story about Aurora. Somebody said that they thought they were the only person who had published. Aurora and I have known each other for more than 30 years. We've never published together. We've always talked, but we've never published. And somebody talked at the very beginning about Aurora's elegance. And so to end this, I will going to tell a story about Aurora, which is embarrassing to me, not to her, by the way. So I met her at Les Ouches. I visited her a few times in Pittsburgh. I was in Chicago at that time. I then was postdocing at AT&T Labs, and you came in and gave me a seminar at AT&T, and then Aurora was, of course, very elegant. I thought, oh, a very elegant person, so you have to do something nice. I'm not elegant, I'm never elegant, but I do have decent clothes if I need them. And AT&T Laboratories is in New Jersey. It's about 40 miles from New York. And so I was able to arrange an invitation to a fancy reception at the Italian Consul General in New York. And then we had tickets to go to the Metropolitan Opera. And so Aurora always looks like she's going to go to the consulate or the Met. And I dressed up. And I actually had my car serviced so it would be okay, because I had an old General Motors car. And we started driving into New York. And there's a big tunnel, the Holland Tunnel, between New Jersey and New York. In the middle of the Holland Tunnel, my car stops. And the car died because the servicing involved putting in new parts, and they put in a defective part. And so we're sitting in this tunnel during rush hour, being screamed at by all these people. And this tow truck shows up, and it tows us out of the tunnel, so we weren't lynched. We weren't murdered by the people who were being delayed. But it towed us back to New Jersey, not to New York. And then it started snowing really hard. And so they dumped us in this parking lot in a deserted part of New Jersey. We're wearing these evening clothes. And I call the towing company, and we waited 3 hours for tow. And then the car is behind the tow truck, and we're squeezed into this cab of this tow truck going 30 miles back to my house, away from our party in our opera in New York. And Aurora looks at me very calmly and says, you know, I don't think I've ever spent an evening like this before. And so that's my story for Aurora.
You make it actually to the opera?
No, we rebooked it for the next day for the opera, and we missed the party. So unfortunately, I still owe Aurora an invitation to the Italian Consul General in New York. I'm sorry about that. So that was my Aurora story. Thank you very much.
Nice talk. Let's ask a couple of questions if you have. I know it's a little late. Yes.
Can you include in your platform other kinds of models that are, Potts model or these vertex models? Are you willing to do so?
We would love to have people. One of the reasons you write open source software, which is much more difficult technically than writing sort of physicists hard-coded things, is that you would like people to write additional methods. And CompuCell is designed to be modular, so you could actually plug in additional methodologies. So far, we haven't had a lot of people do that. The EPA adopted CompuCell for their computational toxicology program. They wrote a front end for it. Unfortunately, they never got permission to release it, so it's still locked up with the EPA. People have written a few extensions. This new finite element package will be compatible, so it will be usable with this. We've had people write PDE solvers, which we've included in CompuCell. But we'd love to have, if somebody wanted to give us a phase field model or a vertex model or something else to include, we would be delighted to work with people to extend it. Something we really need is a good fluid solver. We talked for a number of years with the Phoenix people, but they're a little bit Linux sort of fundamentalists, and so they weren't really enthusiastic about a Windows project. And so in the end, we didn't work with Phoenix. FE Bio does a lot of very nice things, but it, until recently, was not. It was open. It was free, but not open source. Now it's open source, so we might do that. So if there are modules that one thinks would work well with this kind of framework, the system consists of an editor, which is a custom editor which helps you write the code, a player which allows you to run and visualize simulations. Everything is integrated through Python. So if you have if you're Python callable, essentially you could use it immediately. The Python interface slows things down a little bit, not too much, but it does mean that it's very flexible. One of the things that we're going to do relatively soon is allow you to run CompuSelf from Jupyter notebooks instead of Player, so you'll be able to use that kind of notebook environment if you want to. So yes, we'd love to have people who want to write extensions, yes.
More questions?
Yeah, one, thank you. About the last part of the structure of the vascular structure of retina, I was wondering, if I provide you a retina vascular structure that is healthy from a healthy person, this risk map will be empty?
So the assumption that we made, because we didn't have the data at the time, was the following, that to begin with, you always build phenomenological models. And so everything fundamentally is a Hill function, which gives you a stimulus and a response. And then you start by tuning that Hill function to agree with the experimental data to the extent that you can. Ultimately, of course, you want to replace that Hill function with microscopic models of the actual regulatory pathways, but to begin with, you do that. So the way that model was built was we took the vascular pattern we saw, we did a simple Kirchhoff solver flow simulation to calculate the flow, then calculate what we expected the oxygen tension at each surface of the vasculature to be, did a diffusion model on top of that, and then said that the level of hypoxia shouldn't be more than the cells could tolerate. In other words, we knew that in the normal patient there isn't neoangiogenesis, and therefore the level of VEGF has to be below the threshold for that. And so that's how you tune the model. So it's not based on experimental measurements of oxygenation, but since we know that the normal patient doesn't have neoangiogenesis, the level of VEGF has to be below threshold. So we tuned it to be just below threshold. In that case, when you lose something, then you tend to push the oxygenation a little lower, pushes VEGF up, and then you get progression. If we had patient time series, then we can validate those kind of models.
Thank you.
I have a question, if nobody else has questions. This type of vascularization around the macula also happens in old people. It's not only in diabetic people. So I understand that the treatment is that they inject some kind of substance that basically prevents the formation of vessels, no?
Yes.
Some kind of anti-VEGF or
so
something.
So that's also used in diabetic retinopathy.
Have you also treated that with, like in simulations, but like burning sites, or do you think it would work?
So actually, in the interest of time, and actually I raced, so I could even have shown it. My very favorite simulation of all the simulations we did is one of age-related macular degeneration due to choroidal neovascularization, which is what you just described. And in that case, what was interesting was that we did some experimental work too, not really live experiments, but ex vivo. You go and order eyes from the human cadaver eyes, and you could examine them and you could work with those. FedEx did a little experiment for us where somebody sent us an eye where they had filled the tube completely full of liquid. And of course, if you want to homogenize tissue, you put the tissue in a tube which has 1/3 air and 2/3 water, and then you shake it. So instead of an eye, we got flakes. But it was a human eye, and you want to use it even if, a human donor, you want to use the tissue even if it's not in good shape. And so Bas Schrinefeld, who was the leader student of the experiment, is now at medical school, teaching at medical school, said, put it under the microscope, and looked at the flakes and said, it's interesting, where the flakes have delaminated is where there's neovascularization. And so he said, so maybe actually choroidal neovascularization is also an adhesion defect. And so we then built a simulation of choroidal neovascularization based on a growth factor model like the one I showed here, and showed that that could not reproduce the observed etiology of the disease. and then one based on adhesion defects and showed that that could. I remember we went to ARVO, the American Research in Vision and Ophthalmology Conference, as these outsiders. I gave this talk. And there were 10,000 talks about using Avastin to treat this disease, which don't work. We gave a talk saying Avastin can't work because that's not the mechanism of the disease. We thought we were going to be crucified. Actually, they said, really, this was nice because we knew that what we were doing doesn't work. And a little bit later, somebody actually did an experiment which showed that there was, in fact, an adhesion defect which was causing this problem. Basically, this is not the vasculature on the surface of the retina. This is vasculature behind the retina. It's kept out of the retina by the adhesion between the pigmented retinal epithelial cells and Bruch's membrane. As you age, because of an evolutionary design error in rhodopsin 400 million years ago, your eyes have to keep reforming rhodopsin. They have to get rid of the breakdown products. That has to go through Bruch's membrane to be taken out by the vasculature. And you get lipids accumulation on Bruch's membrane as you age, which is not cleared up. Of course, if I want to glue something to a surface, I don't cover it with soap before I glue. And so as you age, the adhesion of the pigmented retinal epithelium to the substrate gets weaker. This is why one of the reasons that old people are more susceptible to retinal detachment when they have a blow to the head. And that eventually in some people gets weak enough, the blood vessels actually are always trying to get into the retina, but they're normally kept out by this barrier. As you age, that barrier gets weak enough. Once the vessels can get in, if they can push through, you're in a low oxygenation, high VEGF region, they proliferate rapidly. And so it's actually a physical barrier failure that seems to be the cause of that condition. The difference is I don't really know how to treat. I don't know how to improve the adhesion there. This one, I think I know how to improve the treatment. So thank you for the question.
Okay, thank you very much for the nice talk. So do you want to close the symposium?
Yeah.
Careful.
I want to declare this symposium closed. But before doing that, I would like to thank all of you who had made this occasion, from my point of view, memorable. Yes, and I think from today we will get new friends and new enemies. So, yeah. So, thank you very much for coming, and have a very good time, or your remaining time in Mexico and beyond. Thank you.
Da instrucciones para el restaurante. Va a venir el camioncito para llevarlos a
Sí,
la playa.
sí. There will be. La camioneta que los ha traído a los invitados va a estar.